Which theoretical technologies proved decisive for effective planetary defense? How did the near miss reshape global policies on future planetary defense collaboration? How will this success influence long-term investment in space infrastructure and asteroid monitoring programs? By the following morning, the discovery had set urgent wheels in motion. In observatories and space agency offices around the world, phones rang and quiet conversations unfolded in pre-dawn light. The astronomers who first calculated the asteroid's trajectory reached out to colleagues on other continents, sharing data and asking for independent confirmation. One by one, telescopes elsewhere were turned toward the patch of sky where the intruder lurked. Within hours, fresh observations verified the alarming truth. An asteroid roughly a kilometer across was indeed on a collision course with Earth, projected to hit in just over a year's time. The probability of impact, once a mere abstract concept rehearsed in tabletop exercises, was now nearly certain and dated on the calendar. In those first tense hours, the information was kept confidential among scientific and government circles. International protocols dictated that heads of space agencies and national governments be informed promptly. A flurry of encrypted messages and early morning phone calls connected leaders who rarely spoke, uniting them in stunned silence as they learned the news. Imagining the weight of those conversations is sobering. A scientist calmly explaining orbital diagrams and impact probabilities to presidents and prime ministers jolted from their sleep. Many of these seasoned leaders, who had faced wars and crises, found themselves momentarily speechless at the gravity of the news. There was no room for doubt or delay. Plans had to be laid in secrecy before alarming the public. All agreed. The world would soon need to know. But first they had to grasp the situation fully themselves and coordinate a response. It was not long before the wider world learned of the threat looming in space. After hasty consultations, global leaders agreed to present a unified message. Within a couple of days, an extraordinary joint announcement was broadcast simultaneously from major capitals. People around the globe paused their daily routines to watch as their leaders, somber and resolute, appeared on screens, each speaking a part of the same prepared statement. In plain terms, they explained that a large asteroid had been discovered on a path that could strike Earth in the foreseeable future. They shared what was known: the asteroid's approximate size, the projected date of closest approach, and the efforts underway to refine the details. The tone was careful and measured, aiming to inform without inciting panic. Translators echoed the message in dozens of languages. The news transcended all borders. For the first time in human history, every nation and every person faced the same impending challenge together. In the wake of the announcement, experts provided more insight about the asteroid itself. It was officially designated with a catalogue number, but many simply dubbed it the asteroid, with a fearful respect. Preliminary observations suggested it measured on the order of a kilometer across, a craggy dark rock left over from the solar system's youth. It was hurtling through space at about 30 kilometers per second relative to Earth. If such an object were to strike, scientists warned, it could release energy millions of times greater than the most powerful human-made bombs, enough to cause global devastation. This stark truth underscored the urgency of the world's efforts. Never before had modern civilization confronted a natural threat of this magnitude with so little warning, and yet never before had we been so prepared to meet the challenge head-on. On the day of the public announcement, that same young astronomer found herself sitting with her family in front of the television, listening as the world was told of the danger she had helped uncover. Her parents glanced at her with concern and pride, noticing the tear she wiped from her eye as the unified message played out. She felt a strange mix of fear and responsibility, knowing better than most the weight of those carefully chosen words. When her younger brother nervously asked if they would be okay, she managed a reassuring smile and pulled him close, silently vowing to do everything in her power to make sure the answer was yes. In living rooms, offices, and city streets, the response to the announcement was a collective gasp of disbelief, followed by an eerie stillness. In a bustling cafe, conversations hushed mid-sentence as customers crowded around a television. In a remote village, an elderly couple listening by radio clutched each other's hands. For a few heartbeats, the whole world seemed to hold its breath. Then came the questions, the murmurs, the rush to contact loved ones. Strangers found themselves turning to one another for reassurance. In homes, parents knelt in front of wide-eyed children, answering their questions with gentle reassurances, even as their own voices trembled. Television and radio channels replayed the announcement over and over, and experts were brought in to explain what it all meant. Initial fear slowly gave way to a grim resolve in many. If this was truly a danger to all of Earth, then all of Earth would have to face it together. In the days that followed, humanity's collective ingenuity was marshalled at breakneck speed. Top scientists, engineers, and military strategists from every major nation convened in virtual meetings around the clock. They dusted off old contingency plans for asteroid threats, plans that had only existed on paper and in computer models until now. Every option was on the table: launching spacecraft to nudge the asteroid's trajectory, attempting to break it apart, or preparing Earth for impact if deflection failed. Specialists calculated and debated, their faces drawn but determined as they pored over simulations of the asteroid's orbit and the physics of various intervention strategies. What had been theoretical exercises for decades had suddenly become a very real, very urgent project. And unlike so many challenges in the past, this was one that clearly transcended politics and borders. In those meetings, there were no separate flags or nations, only human beings focused on a single crucial task. Before long, a consensus emerged on the best course of action. Earth's spacefaring nations would mount a direct mission to intercept the asteroid and try to alter its course. Multiple launch vehicles were repurposed and fast-tracked for this emergency. Rockets that had been meant for routine satellite deployments or lunar missions were reassigned to carry the hopes of the planet. The plan was ambitious and twofold. First, a pair of robotic spacecraft would be launched to rendezvous with the asteroid as early as possible. One would collide with the asteroid at high speed, acting as a battering ram to nudge its trajectory. The second, carrying a powerful nuclear device, would follow closely behind. If the kinetic impact proved insufficient, the second craft would detonate its payload near the asteroid, attempting to push it further off course with the force of the explosion. These drastic measures had been studied in theory, but never tried in practice on such a scale. Yet now, there was no hesitation in committing to them. At the same time, Earth prepared for the worst-case scenario. Disaster management teams quietly began identifying which cities and coastlines might need evacuation and stockpiling food, water, and medical supplies in case the deflection failed. Months of feverish preparation led to the day of launch. On a clear morning at a Cape Canaveral launch site, one of the most powerful rockets ever built stood poised against the sky. Around the world, people tuned in to watch live footage as the final countdown clock ticked away. Engineers and dignitaries crowded the control rooms, their faces tense but hopeful. At the final moment of the countdown, the rocket's engines ignited with a blinding flash, and a thunderous roar rolled across the coastal flats, shaking the ground for miles around. Slowly at first, then with gathering speed, the massive vehicle rose upward, trailing a brilliant plume of white toward the heavens. Not long after, other launches followed from distant cosmodromes, sending additional interceptors on their way. The journey had begun, a race between our technology and the oncoming asteroid, unfolding millions of kilometers above us. At the launch site, the young astronomer who had first spotted the asteroid watched in awe, tears on her cheeks as the rocket climbed. Far beyond, across continents, cheers and prayers mingled as the spacecraft carrying humanity's hopes vanished into the blue sky and then to the starry beyond. After the flurry of launches, a hush settled over the world's efforts. Now came a period of anxious waiting and careful monitoring. The interceptor spacecraft, mere specks of metal against the vastness of space, sped toward their rendezvous, guided by the precise mathematics of orbital mechanics. Mission control centers around the globe tracked their progress relentlessly. Weeks passed, then months. Autumn turned to winter, winter to spring, and all the while that knowledge hung over every moment. People went to work and school, tended fields and shops, but in the back of every mind was the awareness of the silent missile on its way. Life continued, yet everything felt touched by the knowledge of what was coming. It was a time of suspended breath, a tense quiet, a countdown not of minutes or hours, but of many long weeks, as humanity waited and watched. The sun still rose and set as usual. Rain fell, winds blew, and nature carried on indifferent to the coming peril, even as human eyes remained fixed on the skies. News outlets provided sober updates. The spacecraft were on course, their systems healthy, their trajectory corrections executed flawlessly. On screens, animated diagrams showed the shrinking distance between Earth, the outgoing spacecraft, and the inbound asteroid, 3 dots moving in a cosmic ballet. Finally, the moment of first contact arrived. 18 months after its discovery, the rogue asteroid had crept to within just a few million kilometers of Earth, close enough for the interceptors to do their work. In a mission control room in California, filled with hushed engineers and scientists, a wall-sized screen displayed the live feed from the lead spacecraft's camera as it closed in. At first, only darkness and stars were visible. A soft voice on the headset calmly called out the closing distance. A few thousand kilometers. A few hundred. Then, a tiny dot appeared at the center. The asteroid, reflecting a faint sunlight. Frame by frame, the dot grew into an irregular, mottled rock, its surface scarred with craters from eons of cosmic history. Gasps of awe and tension filled the room. They were seeing their target up close for the first time. The spacecraft hurtled onward, autopilot steady and true, aiming for a precise collision at a pre-calculated spot on the asteroid's sunlit side. 50 kilometers, 20 kilometers, 10. The final image transmitted showed nothing but the rocky ground rushing up. And then, static. The screen went blank. A beat of silence followed. Then a wave of joyful applause and tears. At the back of the control room, the young astronomer buried her face in her hands for a moment, overwhelmed by relief. Outside the control center, technicians hugged each other. Similar eruptions of relief and cheering broke out in living rooms and public squares worldwide. The little craft had obliterated itself against the asteroid, imparting a slight but crucial push. Engineers immediately turned their eyes to the data pouring in from radar and telescopes, eager to measure how much that push had changed the asteroid's path. By design, the little craft had sacrificed itself to give Earth a chance. Hours after the impactor's collision, preliminary data came in. The asteroid's speed had changed, but only by a modest amount. Instead of a direct bullseye with Earth, the new trajectory looked to be slightly off-center, a graze that might still cause catastrophic damage. It was a partial victory, but not enough. Mission controllers sent the command to the second spacecraft, which had been trailing behind the first. On cue, it adjusted course to position itself alongside the asteroid, carrying out a delicate dance to match the rock's velocity and orientation. Once in position, and at a safe standoff distance, the craft armed its warhead. The world braced a second time. At the planned moment, a silent burst of light was captured by distant telescopes. The nuclear device had been detonated as intended. For a few moments, the asteroid was enveloped in a brilliant cloud of vaporized material and dust. When the glow subsided, observers eagerly waited to see what remained. Had the explosion nudged the asteroid further, or fragmented it, or both? Over the next few days, astronomers painstakingly plotted the asteroid's new course. With each additional measurement, hope grew. The double strike appeared to have worked. Projections now showed the asteroid missing Earth. Not by a comfortable wide berth, but by enough that it would not strike the planet's surface. It would be an exceedingly close shave on the cosmic scale. The asteroid would pass perhaps within the realm of high-altitude satellites, but a miss nonetheless. There was a collective sigh of relief among the scientists and officials tracking the numbers. Cautiously, they shared the good news with the public. The worst-case scenario seemed to have been averted. Still, they warned, the world wasn't entirely out of danger yet. The asteroid might have shed some fragments during the explosion, or from the stresses of its altered path. Any such debris could be on its way toward Earth, and might arrive at roughly the same time as the asteroid's flyby. In response, radar systems and telescopes scanned even more intently for any sign of smaller objects trailing or accompanying the main rock. The final countdown to the asteroid's approach turned into a peculiar global vigil. In the hours before its nearest pass, millions of people stepped outside to look at the sky, hoping for a glimpse of the celestial visitor. The asteroid had brightened enough to be barely visible as a moving star in the night for those who knew where to seek it. Many others watched through broadcasts from observatories. In some cities, public viewing events were held with telescopes pointed skyward. Professional astronomers guided anxious crowds as they tracked the object as it hurtled past the moon's orbit toward Earth. Among them, the young astronomer had returned to her hometown, setting up a small telescope in a local park to help her community see the faint streak of the asteroid against the stars. There was tension, but also a strange sense of wonder. Here was a mountain of space rock, once destined to strike our world, now slipping by it in the void. All around the world, prayers and wishes were offered under open skies. Families held hands on their front lawns, and strangers became companions for a night as they scanned the heavens together, united in their awe and anxiety. At last, the predicted hour arrived. The asteroid, invisible to the naked eye during daylight, swept closest to Earth just after dusk over one hemisphere, and under the stars of midnight in the other. At its nearest, it skimmed well within the moon's orbit, closer than some satellites, racing past at tremendous speed. Telescopes around the world locked onto it, relaying images of a fast-moving dot gliding against the starry background. Then came a sight no one would ever forget. As the asteroid reached its point of nearest approach, the sky lit up with a cascade of shooting stars. Earth was not entirely untouched after all. Dozens of pebble-sized fragments, likely shaken loose from the asteroid's surface by the recent explosion, were burning up in our atmosphere. They etched brilliant streaks across the twilight sky, each one met with gasps of amazement and tears of relief. These meteors flashed, and then were gone, fizzing out high above before any harm could be done. It was as if the universe had arranged a celebratory fireworks display to mark the occasion. Moments later, the asteroid itself had passed, continuing on into the dark beyond Earth, gradually diminishing from view. The danger was over. A collective exhale of relief can almost be felt. Dawn broke the next day on a changed world. Though the streets and fields looked the same, and life soon resumed its familiar rhythms, there was a fresh current of gratitude and wonder in the air. Across nations, people celebrated in whatever ways they could. Some gathered in churches, temples, or open squares to give thanks. Others held quiet dinners with family, cherishing their company a little more than before. Scientists and engineers, exhausted and exhilarated, finally allowed themselves to breathe and smile, hailed as heroes by strangers on the street. For a brief, shining moment, humanity had acted as one and prevailed. In the aftermath, leaders spoke of cooperation and vigilance. Programs to scan the skies received renewed support and funding from a now keen public. School children around the world learned the story of how humanity had stood together under the threat from the heavens and turned it away. Pieces of the asteroid, tiny meteorites that had fallen harmlessly, were collected and displayed in museums, a tangible reminder of the challenge that was overcome. They sparkled darkly behind glass cases, whispers of the void that nearly changed our world. At one exhibition, the young astronomer stood anonymously among the crowd, gazing at a fragment no bigger than her palm. She wondered how something so small and ordinary-looking could carry so much significance. In that silent moment, she felt both proud and humbled, knowing that in the grand story of humanity's brush with disaster, she had played a part. People from all walks of life would visit and gaze at those space rocks, reflecting on how close they came and how extraordinary it was that in the end, Earth endured. That night, under a sky once again calm and indifferent, the stars shone as they always have. But those who looked up felt a renewed connection to one another and to the cosmos itself. We had faced the darkness and come out the other side. The universe would continue to send its wandering messengers, but now we knew we could answer them, not with fear alone, but with knowledge, unity, and hope. The young astronomer stepped out that night and looked upward as she had countless times before. The stars winked back calmly, and she found herself smiling. In their eternal glow, she felt a promise that whatever challenges came from the cosmic deep, humanity would face them together. And so, as the earth turned quietly beneath the heavens, humanity carried on, wiser and humbled, ever vigilant beneath the eternal twilight of the stars. In the immensity of the cosmos, time stretches out beyond human comprehension. Stars are born and die, planets form and crumble, and sometimes, in a mere blink of that cosmic timescale, the course of life on a planet can change forever. Our own Earth, with all its life and history, is no exception. For as long as our planet has existed, it has been bombarded by fragments of ancient asteroids and comets wandering through space. Most of these cosmic visitors are small and burn up harmlessly in the upper atmosphere, streaking across the night sky as tranquil shooting stars. But on very rare occasions, a larger wanderer comes calling, one big enough to punch through the atmosphere and strike the ground with catastrophic force. It only takes one such impact on the wrong day to turn paradise into apocalypse. To understand the threat that such impacts pose, we must journey back into Earth's deep history. We will visit moments when our world was violently remade in an instant, moments when the sky truly fell and life's story was irrevocably changed. In the stillness of prehistoric skies, destiny arrived on a collision course, and nothing on Earth would ever be the same again. Picture Earth as it was 66 million years ago, late in the age of dinosaurs. It is a warm, sunlit world near the end of the Cretaceous period. Lush, semi-tropical forests and flowering plants carpet the land, and swamps teem with life. Towering dinosaurs, Triceratops and Edmontosaurus among them, roam across broad river valleys, while tyrannosaurs prowl in the shadows. The oceans are warm and shallow, filled with ancient reptiles and coiled ammonites thriving under blue-green waters. Overhead, pterosaurs with wingspans like small planes glide on thermal winds. It is a tranquil morning like any other. Gentle waves lap at a fern-lined lake, and dragonflies flit through the humid air. A hadrosaur lifts its head from a stand of cycads, chewing slowly, sensing nothing amiss. There is no sign that this day will be any different from the millions that came before. But high above the atmosphere, far beyond where any creature can see, an enormous visitor is approaching at unimaginable speed. Far out in space, an asteroid perhaps 10 kilometers across has been knocked from its old, stable orbit eons ago. Now it barrels towards Earth, a dark mountain of rock and metal hurtling silently through the void. For millennia, it has wandered the solar system's cold outer reaches, unseen and insignificant. But guided by gravity and fate, it is now on a perfect collision course with our planet. As it enters the upper atmosphere, the asteroid ignites into a furious fireball. To any creatures below, it would appear as a second sun streaking across the sky, brighter and hotter than anything they have ever witnessed. A searing streak of light grows rapidly, tearing through wisps of cloud with a thunderous roar. In its final moments, this massive intruder screams over the Gulf of Mexico, trailing a wake of fire. On the ground, dinosaurs might pause in bewilderment, casting their gaze upward. Perhaps a triceratops hears a distant rumble like never before, or a flock of pterosaurs veers off course in panic. But there is no time to truly comprehend the horror blazing down upon them. In an instant, and with a force beyond imagining, the asteroid strikes Earth. One moment, the shoreline of a lush tropical sea is calm. The next, it is as if the sun itself has exploded on the horizon. The impact occurs near the coast of what will one day be the Yucatan Peninsula of Mexico. In that split second of collision, the asteroid and a chunk of Earth's crust vaporize in a flash of blinding light. A white-hot fireball erupts, hotter than the surface of the sun, annihilating everything in its vicinity. The ground shakes violently, a global earthquake radiating out from the impact site. The entire planet rings like a bell. A massive crater begins to form as the bedrock itself behaves like liquid, splashing upward and outward. Within moments, a yawning hole nearly 180 kilometers across gouges into the Earth, the newborn Chicxulub crater. A towering plume of debris punches up through the atmosphere and into space, carrying with it the vaporized remnants of land, sea, and asteroid. Where there was paradise, now there is only an apocalyptic blast zone. All around the impact site, life is instantaneously obliterated. For hundreds of kilometers in every direction, forests are flattened and charred to ash in the blink of an eye. An intense shockwave, a wall of superheated air, radiates outward, flattening giant cycads and conifer trees like blades of grass. Every living creature in its path is torn from the ground and seared by heat. A heartbeat later, a towering wall of water rises from the nearby ocean as the sea itself is heaved up. This mega tsunami, hundreds of meters high, races toward distant coastlines. Within hours, shores 1,000 kilometers away will be scoured clean by waves that defy imagination. Meanwhile, molten rock and vaporized debris from the impact are blasted high above the atmosphere and begin to rain back down. Across the hemisphere, the sky turns into an incandescent shower. Millions of red-hot boulders and glassy droplets of molten earth streak back through the atmosphere, igniting vast wildfires wherever they land. Within minutes, whole forests on continents far from the impact are set ablaze by this fiery hail, It is as if the very air has turned into an oven. For creatures on the opposite side of the world, the cataclysm is not immediate, but their doom is sealed all the same. In the days and weeks following the impact, fine dust and soot high in the atmosphere spread like a veil around the entire globe. Sunlight is blotted out by a dark pall of debris. What was midday turns to twilight, and then to an endless starless night. The world begins to cool rapidly under this sun-blocking shroud. Photosynthesis falters and then stops. Plants wither in fields and forests, deprived of life-giving light. Temperatures plummet as an impact winter sets in. Firestorms that raged from the raining debris finally burn themselves out, and thick smoke joins the dust in the skies. When moisture condenses and falls, it comes down as toxic rain. The asteroid struck rocks rich in sulfur and limestone, launching sulfate aerosols that now mix with clouds. Raindrops turn to mild acid, hissing as they fall on charred leaves and into lifeless seas. The once bright, warm Earth has become a cold, dim, and poisonous world. Week after week, the darkness persists. Temperatures around the planet fall to near freezing, even in what was summer. The lush landscapes of the Cretaceous become cold, barren wastelands shrouded in perpetual twilight. Hunger and desperation spread among the survivors. On land, the great herds of plant-eating dinosaurs find nothing to eat as the vegetation dies off. The last towering sauropods and horned dinosaurs weaken and collapse, having consumed the final withered ferns and pine needles. Predatory dinosaurs, too, starve as their prey disappears. Many probably froze to death in the bitter chill that followed the blast. In the oceans, without sunlight, algae and plankton, the base of the food chain, perish in massive numbers. Coral reefs bleach and die. Large marine reptiles, like the mosasaurs and plesiosaurs, struggle to find food in dying seas. In this prolonged global night, an estimated 75% of all species on Earth quietly slip into extinction. The mighty dinosaurs, who had dominated the land for over 150 million years, perish one by one. Enormous tyrannosaurs that once shook the ground with their footsteps now lie motionless in drifts of ash. Winged pterosaurs that ruled the skies fall to earth and vanish. Marine reptiles, from long-necked plesiosaurs to the great mosasaurs, disappear beneath the dark, toxic waves. Yet not all life dies in this apocalypse. A few living things find refuge and carry on, like sparks of hope in the darkness. Some small mammals, no larger than rats, survive by sheltering deep underground in burrows. There they huddle together, sustained by cached seeds and roots, waiting out the dark winter above. Tiny shrew-like creatures tunnel through cold soil, finding insects and worms to eat when nothing else is left. Birds, the only dinosaurs to ultimately outlive the cataclysm, endure by eating whatever they can, perhaps seeds from the last dried pods or the grubs burrowed in dead wood. In the seas, some hardy creatures persist around thermal vents in the deep ocean or in pockets of water that remain somewhat productive. Not all ecosystems are completely snuffed out. Along certain coasts, a few resilient species of fish, clams, and crabs survive on detritus and darkness. Slowly, over years, the dust and ash in the sky begin to settle. A pale sunlight finally pierces the gloom once more. Green shoots of ferns, nature's pioneering plants, start to poke up through the ashy soil, covering the devastated ground like a thin green carpet. Life, fragile but stubborn, is beginning to recover. The age of the dinosaurs has ended, but a new chapter in Earth's story is dawning, one that, many millions of years later, will lead to us. That fateful impact at the end of the Cretaceous is now known as the Chicxulub event. It marks the boundary between the Cretaceous period and the Paleogene, a thin, dark line in the geological record that can be found all around the world. For a long time, scientists could only wonder what had caused such a sudden die-off in the fossil record. The idea that a rock from space could essentially erase most life on Earth in a geological instant seemed like science fiction. But clues hidden in the Earth's crust eventually told the tale to those who knew how to read them. In the late 1970s, a team of researchers led by physicist Luis Alvarez and his son, geologist Walter Alvarez, were studying ancient sedimentary layers in Italy when they discovered something astonishing. A thin band of clay, exactly at the dinosaur extinction level, that was enriched with the element iridium. Iridium is very rare on Earth's surface, but relatively common in meteorites. The same mysterious iridium layer was soon found at dozens of other sites worldwide, all dating to the end of the Cretaceous. It was as if a fingerprint from the crime scene had been left in stone, pointing unmistakably to an extraterrestrial culprit. The iridium discovery set off a worldwide hunt for the missing crater, the smoking gun of the impact. If a meteor big enough to wipe out the dinosaurs had struck Earth, where was the crater? At first, many suspected it might have been lost to erosion or hidden beneath the ocean. For over a decade, the source of the iridium remained a tantalizing mystery. Then, in the early 1990s, geologists examining oil exploration data in the Yucatan region of Mexico noticed a curious semicircular pattern in measurements of the Earth's gravity field. By drilling into the sediments there, they found telltale signs: grains of quartz that had been shocked by incredible pressures, and beads of once molten rock called tektites. It turned out a gigantic buried crater, more than 180 kilometers across, was hiding beneath the jungles and coastal shallows of the Yucatan. This was the scar of the impact, the long-sought Chicxulub crater, named after a nearby village. Its discovery confirmed beyond all doubt that an enormous extraterrestrial object had struck Earth 66 million years ago, unleashing the global catastrophe that ended the Mesozoic era. The day the dinosaurs fell was perhaps the worst day life on Earth has ever known. Yet paradoxically, in the long run, that terrible day opened the door for new life to flourish. In the devastation's aftermath, with the great reptiles gone, the world that emerged was very different. Tiny mammals, which had eked out quiet existences in the nooks and crannies of a dinosaur-dominated planet, suddenly found themselves in an emptier world full of opportunity. Freed from the shadow of giants, these furry survivors began to diversify. Over the millions of years that followed, mammals evolved into myriad forms: primates in the trees, whales in the seas, hoofed and pawed creatures roaming the rejuvenated plains. Eventually, one lineage of those small survivors would lead to us, human beings. It is humbling to realize that without that one catastrophic cosmic accident, the evolutionary path that led to humans might never have unfolded. Our very existence, the rise of mammals, and ultimately of humanity, is tied to an ancient disaster. The Chicxulub impact stands as a stark reminder that the threads of life's story can be abruptly cut and rewoven by forces far beyond our control. Earth has endured many such blows in its long history, before and since Chicxulub, though none that we know of have been quite as devastating as the one that ended the age of dinosaurs. For us humans, the extinction of the dinosaurs remains the ultimate cautionary tale, a bad day from the sky that changed the world. But unlike those hapless prehistoric creatures, we have an advantage: the ability to learn from past events and anticipate future ones. We can study the craters and the layers of ash in the geological record and recognize them for what they are: ancient warning signs. Part of preparing for our future is accepting that impacts, however rare, have happened and will happen again. And such disasters are not confined to the distant past or to the realm of geologic time. Even within human memory, our planet has felt the fiery touch of objects from space. These smaller cosmic events lack the world-ending scale of Chicxulub, but they still pack a tremendous punch, enough to flatten forests and strike fear across whole regions. They serve as reminders that Earth is still in the cosmic crosshairs. One such event occurred not in the Age of Monsters, but just over a century ago, within the lifetime of our great-grandparents, in a remote corner of Siberia. It was early morning on June 30th, 1908, in the remote Siberian wilderness, near the Podkamenaya Tunguska River. The summer sun had barely risen above the horizon, and the dense taiga forest was quiet and still under a pink dawn sky. Indigenous Evenki herders were tending their reindeer amid the misty bogs, and a few Russian traders at a distant trading post prepared for another day. All was calm in this isolated corner of the world. In the forest, birds chirped softly, and a herd of reindeer grazed among the birch trees, unaware of any danger. Then, at approximately 7:14 a.m., the sky to the north suddenly ignited. A brilliant point of light, as bright as the sun, streaked across the heavens. It grew rapidly, searing white and blue, leaving a trail of flame. The morning calm was shattered by an immense flash, as if the sky itself had exploded. An eyewitness named Semyon Semenov, sitting on the porch of the trading post 40 miles away, later described how the sky split in two, and high above the forest, the whole northern part of the sky appeared covered with fire. He felt a wave of heat roll over him, so intense he thought his clothes might ignite. Then came a blast of sound, a mighty boom that tossed him from his chair and blew out windows in the cabins around him. For hundreds of miles in every direction, people heard a series of thunderous explosions echo across the countryside. In that moment, day turned to night as the heavens erupted in flame and sound. At ground zero, deep in the Siberian forest, the effect was beyond catastrophic. In an instant, a fireball had detonated a few miles above the ground with the energy of a large nuclear weapon. A tremendous column of fire and smoke burst upward, and a shockwave blasted the forest beneath with unimaginable force. The trees directly below were charred black and stripped of their branches. For miles around, an estimated 80 million trees were snapped like matchsticks and laid out flat, radiating outward from the blast's epicenter. Any animals in the vicinity would have been vaporized or blown off their feet and killed instantly. The ground shook violently. Seismographs thousands of miles away registered the tremors. The earth itself shuddered from the force of the explosion. In the immediate aftermath, a pillar of smoke and fire towered into the sky. Then silence fell over the scorched land. Fires likely smoldered for hours in the tinder-dry forest, sending up plumes of smoke. An eerie glow lingered in the sky. In the evenings following the blast, skies as far away as Europe turned strange hues of silvery blue. Night skies in London were so bright that people reported reading newspapers at midnight by their light. This phenomenon was caused by high-altitude ice crystals and dust from the explosion, dispersed across the upper atmosphere and catching the sunlight long after dusk. The world at large did not yet know what had happened in Siberia, but the sky itself carried hints of the fire that had risen over Tunguska. Remarkably, as far as we know, no humans were killed by the Tunguska explosion. a stroke of luck owed to the remoteness of the area. The Evenki nomadic tribes who lived in the region were awestruck and terrified. In their oral histories, they described the event in spiritual terms, convinced that the blast was a visitation by Ogdi, the god of thunder, who had cursed that part of the forest by smashing the trees and killing the animals. For years afterward, the Evenki and other locals refused to venture near the explosion site, calling it a charred and haunted land. To the wider world, the Tunguska event was at first just a curious footnote, distant thunder on the edge of civilization. In 1908, Russia was a vast empire, and communications were slow. News of an enormous explosion in an uninhabited forest barely spread beyond Siberia. Only years later, after the chaos of revolution and war, did scientists make a serious effort to investigate what had happened. For a long time, the cause of the Tunguska explosion remained an unsolved mystery. In 1927, almost 2 decades after the event, a Russian mineralogist named Leonid Kulik finally led an expedition into the Tunguska region to seek answers. After an arduous trek through swamps and mosquito-infested taiga, Kulik's party reached the blast zone. They could scarcely believe what they saw. Mile after mile of forest was flattened in every direction. Trees lay aligned in tidy rows, all pointing away from a central ground zero, as if a giant hand had swept them down in a circular pattern. As they moved closer to the suspected epicenter, they found trees standing upright, but completely scorched and branchless, like a forest of bare telegraph poles. Kulik searched for a meteorite crater, or fragments of an asteroid, but found none. The absence of an obvious impact crater puzzled him. He guessed, correctly as we now know, that the cosmic object must have exploded in mid-air, causing a devastating airburst without leaving a conventional crater. Later expeditions found microscopic droplets of melted rock and tiny metallic spheres embedded in the trees and soil, minute traces of the cosmic visitor scattered like ashes. Modern scientists estimate that the Tunguska explosion released energy equivalent to 10 to 15 megatons of TNT, roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. Had the blast occurred over a city, it would have instantly reduced it to ruins and caused unimaginable loss of life. Instead, by sheer luck, it mowed down remote forest and harmed almost no one. The Tunguska event remains the largest impact event on Earth in recorded history. It was a stark demonstration that even a relatively small asteroid, perhaps only 50 or 60 meters across, can unleash devastating force. In 2013, a much smaller meteor, about 20 meters wide, exploded in the atmosphere over Chelyabinsk, Russia, shattering windows and injuring over 1,000 people with its shockwave. That modern incident, though tiny compared to Tunguska, showed that these cosmic episodes are not confined to history books. They can happen in today's world, over our cities, at any time. Tunguska and Chelyabinsk are wake-up calls, reminders that Earth is still vulnerable to the kind of calamity that ancient peoples feared, and that we must take the threat seriously. For billions of years, Earth has endured such cosmic assaults, and each time, the planet slowly recovered, though the world that emerged was never the same as before. In the heart of Australia, Aboriginal elders recount a tale of a fire devil that once fell from the sun. They warn never to drink from certain waterholes in the desert, for that is where the fiery spirit plunged into the earth. According to the old story, the fire devil came roaring out of the sky, killing everything in the area and poisoning the land with its burning presence. For thousands of years, generation after generation remembered this event and kept their distance from the cursed site. The night that Fire Devil fell, says the tale, the ground shook and flames devoured the earth. The elders describe how the air itself became hot and bitter, and the sky turned red. Such was the wrath of that fiery spirit that people and animals died where they stood. This warning was passed from parent to child for centuries untold, so that no one would forget the day the sky burned the land. In modern times, scientists discovered that very place, the Henbury meteorite craters in the Northern Territory. About 4,700 years ago, a meteor filled with iron broke apart above the ground there, scattering molten fragments across the land. It gouged roughly a dozen craters into the red earth. The Aboriginal tale precisely described the aftermath: water in the depressions, filled with iron, and death to anyone who dared approach. Somehow, an oral tradition preserved the memory of that ancient impact across 50 centuries. The craters are now quiet hollows in the ground, some filled with rainwater. But the Aboriginal people still knew to avoid them, long before any scientist suspected their true origin. It is astonishing to think that a memory of an event so many millennia ago could remain alive in oral tradition. Yet here it was, an accurate testimony of a prehistoric cosmic strike. Half a world away, in northern Europe, there is an old Finnish epic poem that speaks of a stolen sun and a spark falling from the sky. In the Kalevala, Finland's national epic saga, a wicked sorceress steals the sun, plunging the world into darkness. The sky god Ukko orders a new sun to be made from a spark. The maiden of the air begins to fashion a new sun, but she drops the fiery spark. It plummets from the heavens, lands in a lake, and causes the water to boil and foam. The heroes of the epic see the ball of fire falling somewhere behind the Neva River, to the northwest, in the direction of Estonia, and set off in that direction to seek the fire and restore light to the world. For ages, this was thought to be just a fanciful story. But in the mid-20th century, geologists confirmed that a group of mysterious lakes on the Estonian island of Saaremaa were in fact impact craters. The largest, called Lake Kali, was formed roughly 3,500 years ago, when an iron meteor fragmented and struck the Earth. It incinerated forests for miles around, and surely would have been witnessed by Bronze Age people in the region. The local memory of a blazing fireball and a lake that boiled over seems to have survived in the folklore. The Kali crater was even regarded as a sacred site in antiquity, perhaps because the people sensed that something extraordinary had happened there, an event literally of cosmic origin. Throughout the ancient world, many cultures recorded tales of flames or stones falling from the sky. Often they attributed these to the anger of gods or the judgment of heaven. In the Middle East, the biblical story of Sodom and Gomorrah tells of two cities said to be destroyed by burning sulfur and fire sent from the sky. To the devout, it was divine wrath. To skeptics, it was merely a moral allegory. In recent years, however, archaeologists excavating a Bronze Age city near the Dead Sea, a site called Tall El Hammam, found evidence of a sudden, extreme destruction around 3,600 years ago. Buildings were flattened and melted, pottery surfaces were flash-fused into glass, and a rain of tiny shocked minerals blanketed the area. The devastation was so intense that the city lay abandoned for centuries afterward. The researchers concluded that a Tunguska-sized airburst, an exploding meteor in the atmosphere, was the likely cause. Although debate continues, it is tantalizing to think that the tale of Sodom's fiery end might be a cultural memory of a true cosmic disaster witnessed by ancient inhabitants of the Jordan Valley. One can imagine a survivor from that calamity stumbling out of the ruins at dawn, seeing the smouldering ruins, the air filled with a bitter scent of sulfur and ash, an experience so searing that it became enshrined as a tale of divine wrath. Legends of cosmic calamity appear in many other corners of the world. In China, Old chronicles tell of stars falling from the sky and devastating villages. Native American tribes of the Great Plains spoke of a burning star that crashed to Earth long ago, scorching the prairies, perhaps recalling an ancient impact event or the formation of a crater now lost to time. In Arizona, a giant crater left by an ancient meteor was later discovered by native people who believed only the gods could have carved such a hole in the earth. In the folklore of Siberia, the Tunguska explosion itself became enshrined in legend. The local Evenki people, as we heard, believed it was the furious visitation of their god of thunder. In South America, Spanish explorers in the 16th century learned of a place called Campo del Cielo, Field of Heaven, where indigenous people said a mass of iron had fallen from the sky in ages past. In virtually every region on Earth, one finds old stories of the sky unleashing destruction. From India to Scandinavia, from Africa to the Pacific, stories of falling fires, thunderbolts from the stars, and days of darkness abound. They differ in details and interpretation, yet a common thread runs through them: the understanding that sometimes the sky itself can bring ruin. For a long time, scientists viewed such tales as mere superstition or creative storytelling. But as more evidence of past impacts comes to light, researchers have started to revisit old myths with fresh eyes. A new field known as geomythology examines geological events like earthquakes, volcanoes, and meteor impacts that might lie behind myths and folklore. It is a bridge between science and story. The fiery end of an ancient city, the creation of a crater lake, or the fall of a meteorite shower may all echo through oral traditions. In some cases, the timelines even match. A crater's age aligns with when oral histories say fire from the sky occurred. These overlaps strengthen the idea that our ancestors were not just creating fables for entertainment or moral lessons. In many cases, they were documenting real, extraordinary events in the only ways they knew how. Ancient impact legends remind us that humans have indeed witnessed the sky falling. The fear and awe those events inspired were so profound that they became woven into cultural memory, etched in our earliest stories and myths. Even now, one can imagine generations of our ancestors sitting around campfires, eyes turned occasionally to the starry sky, recalling the time when a star came down and brought ruin. Thousands of years later, we are finally able to connect the dots, to link the legend to the crater, the myth to the meteor. It is a humbling realization. Long before modern science, people knew something that we are rediscovering today, that stones can indeed drop from the stars and alter the course of history. Those old stories carry a warning. They whisper to us across the ages, saying, "It happened before, and it will happen again." While myths can preserve the memory of impacts, they cannot show us the full picture. For that, we must turn to the Earth itself. Our planet's rocks and landscapes hold scars from past collisions, some obvious, others buried and subtle. Each impact crater, each layer of shocked and melted rock, is like a page in Earth's diary, telling of a day when destruction rained down. In fact, during Earth's infancy, impacts were far more frequent. Colossal collisions helped shape the young planet. Countless smaller impacts in those early eons may have delivered water and organic molecules to Earth, the seeds of oceans and life. Having listened to the ancient voices, we now examine the silent testimony of the land. The ground beneath our feet bears witness to a violent past written in stone. It's time to uncover those hidden scars and learn what they reveal about Earth's history of cosmic impacts. Indeed, the moon itself may be the product of an ancient impact. scientists theorize that over 4.4 billion years ago, a Mars-sized protoplanet collided with the early Earth. The tremendous blast melted both objects, and debris from that cosmic collision coalesced into our moon. If true, it means one of Earth's first experiences as a planet was a collision so titanic that it nearly destroyed our world. Yet from the wreckage, the Earth-Moon system, as we know it, was born. Travel across the Earth, and you will find places where the ground itself whispers of ancient cataclysms. In South Africa, green hills ring the town of Vredefort in a vast circular formation. These hills are the deeply eroded remains of the largest impact crater on the planet. Over 2 billion years ago, long before even multicellular life existed, an asteroid perhaps twice the size of the one that later killed the dinosaurs thundered down on primordial Earth. The impact gouged out a crater roughly 250 to 300 kilometers across. Though more than 2 billion years of wind, rain, and tectonics have softened its features, the land still bears a giant scar. On that distant day, the blast would have defied imagination. Shockwaves scoured the ground, and molten rock fountained into the sky. Oceans nearby might have been instantly vaporized into steam. Life at the time was only microscopic in the seas. But if any microbes could sense calamity, this was the greatest calamity they ever faced. If a similar impact happened in our world today, it would be an extinction-level event beyond anything humans have ever witnessed. Far to the north in Canada lies another silent testament to cosmic violence. The rocks around Sudbury, Ontario, conceal the remnants of a colossal impact structure nearly 250 kilometers wide, formed about 1.85 billion years ago. Today, the Sudbury Basin doesn't appear crater-like to a casual observer, because eons of erosion and geologic change have altered its shape and partially filled it in. But telltale clues remain. Strange radial patterns in the underlying rocks known as shatter cones, formed by the shock of the impact, and a unique mix of metals scattered through the basin. Deep underground, miners have discovered rich deposits of nickel, copper, and precious metals. These ores were created when the meteor struck and momentarily turned solid crust into molten rock, pooling heavy elements together. In a twist of fate, a calamity from the sky billions of years ago bestowed mineral wealth that humans now benefit from. The Sudbury impact would have blasted debris across what is now North America, and indeed, tiny glassy spherules from the impact have been found embedded in ancient rock layers hundreds of kilometers away, silent witnesses to that ancient blast. Not all of Earth's impact scars are so ancient. Some are relatively fresh and easy to spot. One of the most visually striking is the Manicouagan crater in Quebec, Canada, a nearly perfect ring-shaped lake about 70 kilometers across, clearly visible from orbit. It marks the site of an impact around 214 million years ago, when dinosaurs were just beginning to appear on Earth. Further north, above the Arctic Circle, lies Siberia's Popigai crater, about 100 kilometers wide and dated to roughly 35 million years ago. When a large rock slammed into the graphite-rich ground there, the immense pressure and heat were enough to transform carbon into diamonds. To this day, the rocks of the Popigai crater are laced with trillions of tiny diamonds. It is a glittering aftermath of that day of destruction. Some cosmic collisions may even have come in quick succession. Around 35 million years ago, at the end of the Eocene epoch, two huge impacts occurred within a geologically brief interval. Besides the Popigai strike in Siberia Another asteroid plunged into the shallow sea off the east coast of North America, gouging out what is now the Chesapeake Bay crater in Virginia. Each of these impacts would have thrown vast amounts of dust and aerosols into the atmosphere. Combined, they may have altered the global climate, causing cooling and ecological disruption that show up in the fossil record of that era. This twin calamity is a reminder that the cosmos can, on occasion, deliver not just one blow, but a 1-2 punch. Even more recent in Earth's timeline is the famous meteor crater in Arizona, USA. Though small by comparison to giants like Vredefort or Sudbury, it stands as one of the best preserved impact craters on Earth, and a stark example of how destructive a relatively small asteroid can be. Only about 50,000 years ago, when early humans were beginning to migrate across Africa and Asia, a metallic asteroid, perhaps 50 meters wide, slammed into what is now the Arizona desert. It exploded with the force of several hundred Hiroshima bombs, carving out a bowl-shaped crater, 1.2 kilometers across and over. It's deep. All life for many kilometers around, from any woolly mammoths or giant ground sloths that might have roamed there, to the smallest rodents, would have been annihilated in an instant by the blast. Today, the crater remains almost as it was then, a great gaping bowl amid the rust-coloured plains, reminding us that even a modest cosmic rock can wreak immense havoc if it crosses our path. In fact, scientists have identified nearly 200 impact craters on Earth so far, ranging from gigantic multi-ring basins to small round craters just a kilometer or two across. They dot every continent, from the famous Chicxulub crater, buried under Mexico's Yucatan Peninsula, to the lonely Wolf Creek crater in the Australian outback, to the water-filled Lona crater in India. These known craters likely represent only a fraction of the impacts that have actually occurred. Many impact scars have been erased by tectonic upheaval, swallowed by the sea, or buried under sediments over geologic time. Earth's active geology is constantly reshaping and healing its surface, which is why our planet's face looks far smoother than, say, the pockmarked Moon or Mercury. Yet occasionally, new scars are found in surprising places. In recent years, using satellite radar data, researchers uncovered a hidden 31-kilometer-wide crater beneath the ice of Greenland, evidence of a significant impact that struck perhaps near the end of the last ice age. And in Western Australia, scientists identified an ancient impact structure over 2.2 billion years old, the Yarrabubba crater, possibly the oldest confirmed impact crater on Earth. Each discovery adds another chapter to the story of Earth's encounters with wandering rocks from space. Those encounters have shaped more than just the land. They have influenced the course of life itself. We saw how one impact ended the age of dinosaurs, allowing mammals, and eventually us, to thrive. Some scientists have suggested that other mass extinctions in Earth's history, such as the Great Permian extinction 252 million years ago, may have been triggered or worsened by impacts, though the evidence remains debated. For instance, a massive circular gravitational anomaly detected under the Antarctic ice might mark a huge hidden crater from around the time of the Permian extinction, hinting at a possible impact culprit. Whether or not a meteor finished off the Permian die-off, which wiped out about 90% of marine species, it remains a topic of lively discussion. What is certain is that impacts big and small have repeatedly reset the stage of life. Each time the skies have fallen, the world has been reshuffled, ecosystems destroyed, climates altered, and new opportunities opened for the surviving life to diversify. Standing on the rim of a great crater, or holding a piece of ancient meteorite iron in your hand, you cannot help but feel a profound sense of humility. The earth beneath us carries scars that whisper of unimaginable destruction and subsequent rebirth. from the South African highlands to the Canadian Shield, from the Siberian tundra to the Arizona desert. The evidence of these violent events is all around us, if we know how to look. Our planet's history is written in these scars, in layers of soot buried in rock strata, in quartz crystals cracked by unfathomable shocks, in rings of mountainous rims that once were molten. They are enduring testimony that our world has never been truly safe from calamity, even during the most tranquil of epochs. As we conclude our journey through Earth's tumultuous past, one truth stands out clearly. Cosmic impacts are not freak anomalies, but a recurring part of our planet's story. They have happened before, and they will undoubtedly happen again. Ancient extinctions and firestorms are not merely dusty tales from prehistory. They represent real possibilities for our future, if we are unprepared or unlucky. The cosmic roulette that brought doom to the dinosaurs is still spinning, and one day our number could come up. However, unlike any creature before us, humanity has the ability to foresee this danger, and perhaps even prevent it. The same scientific insight that allows us to read the records of past impacts in rocks and legends also allows us to scan the skies for the next incoming asteroid. We are no longer helpless beneath the cosmic bombardment. Knowing what we know now, we have a responsibility to use that knowledge. The question becomes, what will we do with this warning from history? The countdown to the next big impact is quietly ticking, whether it comes in 100 years or 100,000, and our actions, or inactions, will decide how the next chapter of this story is written. As dusk settles across the world, a quiet vigil begins. In remote deserts and atop volcanic peaks, automated telescopes swivel toward the stars each clear night. They sweep methodically over the darkness, capturing countless pinpoint stars and seeking the faint, telltale motion of something closer, an asteroid wandering through our cosmic neighborhood. This global watchfulness is our early warning system, humanity's ever-growing network of asteroid hunters. Night after night, these robotic sentinels scan the heavens with patient determination, determined to spot potential threats long before they can reach our skies. For most of history, the skies were surveyed only by human eyes and chance discoveries. Now we have built a coordinated international effort to catch incoming space rocks in time. In Hawaii, powerful survey telescopes like Pan-STARRS began photographing wide swaths of the sky, discovering thousands of new asteroids. In Arizona and around the globe, projects such as the Catalina Sky Survey add their eyes to the search, each telescope contributing pieces to a celestial puzzle. Together they have transformed our understanding of near-Earth asteroids. By mid-2025, astronomers had catalogued nearly 38,612 near-Earth asteroids of all sizes. From mountain-sized behemoths to smaller, house-sized rocks. Each discovery is like adding a new entry to Earth's cosmic risk registry, plotting where these objects orbit and ensuring none are on a collision course. Yet even with so many found, scientists know there are thousands more out there, still unseen, looping silently around the sun. Each new asteroid discovery brings both relief and resolve. Most turn out to be harmless, destined to sail past our planet at safe distances for centuries to come. But finding them before they find us is paramount. An important part of planetary defense is finding asteroids before they find us. So if necessary, we can get them before they get us, remarks Dr. Kelly Fast of NASA's Planetary Defense Coordination Office. Her words capture the slightly wry determination shared by those who guard our planet from cosmic intruders. It's a gentle contest between humanity and the universe, a race to spot incoming hazards years or decades in advance, when a small nudge can make the difference between a close miss and a catastrophe. With each sunset, as stars emerge one by one, that race quietly continues on mountaintops and observatories worldwide. From the crisp, thin air of Mauna Kea in Hawaii to the clear, dry nights of the Atacama in Chile, advanced telescopes maintain a near-constant vigil. The ATLAS project, Asteroid Terrestrial Impact Last Alert System, now operates 4 telescopes stationed in both the northern and southern hemispheres, enabling it to scan the entire dark sky every 24 hours. Once only 2 telescopes in Hawaii, ATLAS expanded to include observatories in South Africa and Chile, covering the sky round the clock by alternating hemispheres. Each ATLAS telescope is relatively small, half-meter in aperture, but with sensitive cameras they capture enormous swathes of sky in a single exposure, an area hundreds of times larger than the full moon. Night after night, image after image, computers sift the data for anything that moves against the starry background. On a typical night, they might flag dozens of moving dots. Most will be ordinary main-belt asteroids far away, or perhaps a stray comet gracing the inner solar system. But once in a while, the software will detect something moving just right, a new near-Earth object, perhaps on a path that crosses Earth's orbit. Instantly, alerts go out to the world's astronomers. A potential new NEO has been found. At such times, the global asteroid tracking community springs into action. Professional observatories and even skilled amateurs pivot their telescopes to get follow-up observations on the new object. They measure its position and brightness, helping refine an orbit. Within hours, what was a faint blip becomes an object with a name or designation and a preliminary trajectory mapped around the Sun. Most often, those first calculations show the asteroid will miss Earth by a comfortable margin, now and in the foreseeable future. Everyone can breathe easy and log the find as another success for planetary vigilance. But on rare occasions, initial calculations can't entirely rule out a future impact, or even suggest a small but real chance of one. When that happens, these observers keep tracking night after night, determined to pin down the truth hidden in the rock's subtle motion. In the meantime, news quietly spreads through the planetary defense network, just in case this new discovery proves dangerous. It's remarkable to think how far our asteroid detection abilities have come. A generation ago, in the late 20th century, few systematic searches existed. Large asteroids occasionally snuck up with only days of warning, or even after passing by. In 1989, for example, a 300-meter asteroid famously dubbed Asclepius whizzed past Earth at a distance nearly the same as the Moon's orbit, and was only noticed after it had already gone by. Such surprises underscored our lack of surveillance. In the 1990s, spurred by awareness of past impacts and the sobering realization of how blind we were, NASA initiated Space Guard surveys dedicated to finding the largest near-Earth asteroids. Astronomers around the world turned their focus to the quest. Observatories like Linear in New Mexico began using automated techniques originally developed for military tracking to scan the skies for moving objects. These early efforts bore fruit. By the early 2000s, a majority of the most dangerous, kilometer-sized asteroids had been found and ruled out for any imminent impact. It was reassuring. The species killer rocks seemed to be accounted for. But smaller asteroids, those tens to a few hundred meters wide, remained largely undiscovered and could still unleash tremendous destruction if they struck. And as a dramatic reminder that even modest cosmic visitors can pack a punch, in February 2013, a meteor only about 20 meters across exploded in the atmosphere over Chelyabinsk, Russia, with no warning at all. The shockwave from that undetected asteroid shattered windows in freezing winter, injuring roughly 1,500 people with flying glass. It was the largest impact in more than a century, a jarring wake-up call that underscored the need for better early warning, even for smaller objects. Since then, efforts to expand our detection network have accelerated. Today, the search is truly a worldwide endeavor. NASA's Planetary Defense Coordination Office, established in 2016, helps fund many of the surveys and coordinates US efforts, but it also works closely with international partners. The International Asteroid Warning Network, IAWN, endorsed by the United Nations, links observatories and space agencies across the globe in a common goal. Dozens of telescopes, from professional surveys to university observatories and even backyard telescopes with skilled amateur operators, feed their asteroid observations into a central clearinghouse, the Minor Planet Center. There, all the data is combined to calculate orbits and disseminate any hazard predictions. It is a quietly humming system that underpins our planetary safety, largely invisible to the public, except on the rare days a new asteroid makes headlines. In those moments, this network ensures that we quickly know whether it's a benign near miss or something that merits concern. One important aspect of the detection network is diversity, using different kinds of eyes on the sky. Traditional optical telescopes that see visible light are the workhorses, but they have limitations. They can only operate on clear dark nights, and they cannot see objects coming from the sun's direction because the sky is too bright in sunlight. To cover these blind spots, scientists have turned to space-based observatories. NASA repurposed a space telescope called NEOWISE, which scans the sky in infrared light to look for the heat signature of asteroids. NEOWISE has been especially useful in detecting dark asteroids that don't reflect much sunlight. In infrared, even dark objects glow with thermal warmth against cold space. Since 2014, this orbiting sentry has found hundreds of near-Earth objects, complementing the ground surveys. Building on its success, NASA is developing a new mission called NEO Surveyor. Slated for launch in the late 2020s, NEO Surveyor will be the first space telescope designed specifically for finding hazardous asteroids. By operating in infrared from a vantage in space, it will be able to spot asteroids that are currently hard to detect, including those lurking in the daylight sky near the sun's direction. With this addition, astronomers hope to finally achieve a long-sought goal, discovering at least 90% of near-Earth asteroids larger than 140 meters, those big enough to devastate entire regions if they struck. Congress charged NASA with reaching that 90% inventory goal, and NEO Surveyor's advanced detectors will help get us there. In tandem, ESA, the European Space Agency, is planning its own space-based infrared telescope called NEOMER to be stationed between Earth and the Sun, specifically watching for asteroids approaching from sunward skies. NEOMER is envisioned as an early warning system, particularly for smaller asteroids, around 20 meters and up, that could impact with little notice. If a rock like the Chelyabinsk meteor were on course, NEOMER could spot it, even if it hides in the sun's glare, ideally giving at least weeks of warning, or in worst case, a few critical days. Such advance notice, even on the scale of days, could make a life-saving difference, allowing authorities to evacuate or warn people to stay away from windows before an airburst blows in the glass. Every element of this growing detection network, from huge survey telescopes to space observatories, acts as an extension of our human senses, stretching our eyesight into the cosmos. They turn the overwhelming expanse of sky into manageable pieces to patrol nightly. And they are working. The number of known near-Earth asteroids has been climbing steeply each year as new discoveries pour in. Importantly, Most of the really large asteroids, 1 kilometer or bigger, have been found, over 872 of them as of mid-2025, and none of those currently pose an impact risk. This is a reassuring milestone. Those giant, civilization-ending boulders are effectively off the near-term worry list. Focus now is on the medium-sized asteroids in the hundreds of meters range, which could level a city or small country. Roughly 11,300 of those have been tracked so far, but astronomers estimate around 14,000 more are still out there unseen. These are the ones that concern planetary defense experts the most. Not large enough to spot decades away with absolute certainty, yet big enough to do immense damage if one were to strike. Finding them is literally a race against time. We want to discover each one while it's still years away from any potential Earth encounter, not when it's already closing in. On any given week, dozens of near-Earth asteroids pass relatively close to our planet, within a few lunar distances. The vast majority slip by unnoticed by the wider public. But within the halls of NASA's Center for Near-Earth Object Studies and other monitoring hubs, each close approach is logged and analysed. When an asteroid will come particularly near, telescopes are cued to observe it. Radar dishes may ping it to map its shape and orbit, and scientists refine their predictions. Often these become chances to test our readiness and communication. In fact, NASA's Planetary Defense Coordination Office releases monthly updates with the latest facts and figures on these cosmic encounters. For example, in a recent month, 7 asteroids passed closer to Earth than the Moon's orbit. None hit us, of course, but each was a valuable drill. It shows that our detection systems are catching objects even of modest size as they buzz by. The truth is that small asteroids, tens of meters across, zip past Earth all the time, and a few even enter our atmosphere each year as brilliant fireballs. Most burn up harmlessly or fall in remote areas. Now, thanks to the diligent sky surveys, we occasionally discover some of these very small asteroids just hours or days before they hit, providing a brief window to predict where they'll fall. Atlas, for instance, has spotted at least 2 tiny asteroids just hours prior to impact, 2018 LA and 2019 MO, each only a few meters across, which later burned up in the atmosphere. These were essentially fireball events, not dangerous, but they proved the concept that even last-minute detection is becoming possible. In an ideal scenario, someday soon, no asteroid will be able to enter the atmosphere by surprise. We'd see it coming, however small, and know when and where it will arrive. The tone among astronomers scanning the sky is one of vigilant optimism. They know that at the moment, we have not identified any asteroid that is on course to significantly harm Earth. That is comforting. It means at least in the next few decades, based on everything we've found, we can sleep without imminent doomsday hanging over us. But they also caution that this is no reason to relax our guard. There is a sizable population of undiscovered asteroids still to find. Any one of those unknown rocks could theoretically be the next one that comes uncomfortably close. The goal, as Lindley Johnson, NASA's planetary defense officer, puts it, is to find any possible impactor years to decades in advance so it can be deflected with technology we already have. In other words, time is the critical factor. With enough time, humanity's ingenuity can likely prevent an impact. Without it, we may be forced to endure one. So every clear night spent searching the skies buys us a little more insurance, a little more cosmic foresight. High above in orbit and down in the quiet dark of observatory domes, this search continues diligently. It's a unique global project in that it serves all humanity. A cooperative effort where scientists from many nations share data freely, united by the common desire to protect our one fragile planet. One can imagine them scattered across the world's time zones, each observer picking up where another left off as Earth turns toward night. A telescope in Arizona might track a newly found asteroid until dawn breaks there. Then a telescope in Australia takes over as night falls in the southern hemisphere, ensuring the object is not lost. This relay can continue for days or weeks, until enough data are gathered to securely pin down the asteroid's orbit. Only then will the community rest regarding that object, knowing it poses no surprise threat. And if calculations do indicate a potential impact someday, even if the odds are tiny, that information is quickly circulated to those who need to know, from space agency officials and scientists to government emergency planners. To facilitate this, formal mechanisms are in place. If an unusual risk arises, NASA and other agencies will notify organizations like the International Asteroid Warning Network, which serves as a central hub for distributing information to governments worldwide. There's even an emergency protocol in case a serious impact threat is confirmed, a bit like a global fire alarm for a cosmic wildfire. Thankfully, we've never had to ring that alarm in earnest for a large asteroid. But smaller scale alerts have already happened, serving as good practice. In 2021, for instance, astronomers spotted an asteroid that initially appeared to have a chance of impacting Earth within mere months. For a day or two, it caused a stir among the planetary defense teams. Observatories rapidly mobilized, more measurements were taken, and within 48 hours, the refined calculations showed Earth would be safe. The asteroid would miss. The temporary concern passed, unnoticed by most people, but for those involved, it was a valuable real-world test of the communication and rapid response system that has been built. This nightly vigil for asteroids, though grounded in science and technology, also carries a sense of wonder. The astronomers are not only planetary defenders, but also explorers, charting the unknown. Many of the space rocks they find are relics of the early solar system, pristine chunks of rock and metal that have been orbiting the sun for billions of years. Every discovery teaches us something, perhaps about the asteroid's composition, its rotation, or how it reflects sunlight. There is even a poetry to their names. These objects often receive designations like 2024 AB at first, but those that prove significant get proper names from myth and history. We have asteroids named for ancient gods and famous scientists, all now catalogued in humanity's astronomical records. It reminds us that while asteroids can pose danger, they are also part of nature's grand tapestry. In protecting ourselves from them, we also deepen our understanding of our solar system neighbours. Far from being a source of constant fear, the expanding asteroid detection network is a story of empowerment and vigilance. Think of it as humanity turning on floodlights in a dark, previously unmonitored warehouse. The darkness of space around Earth is now less mysterious in our vicinity. We are increasingly aware of the drifting objects sharing our journey around the sun. There is comfort in that clarity. One can step outside on a starry night, gaze up, and realize that dozens of telescopes are quietly on guard, peering at those very stars and the space between for any sign of a rogue rock coming our way. It allows us to appreciate the night sky's beauty with just a bit more peace of mind. We know that the next dinosaur killer asteroid is not sneaking up on us undetected. We've likely already found it, or we soon will. And for those smaller asteroids that could still pack a punch on a local scale, we're getting faster and better at catching them early. In the stillness of midnight at an observatory, a researcher might sit in a control room, illuminated by the soft glow of computer monitors. Outside, the telescope moves almost silently, performing its precise dance across the heavens. Stars wheel overhead. Each exposure comes in, perhaps revealing a faint moving dot. The researcher marks it, shares it, perhaps feels a thrill. Is it a new discovery? Almost always, these specks turn out to be nothing dangerous. But each one is a piece of knowledge that makes us safer and more informed. In that measured, careful pace, there is a deep sense of purpose. Our species is learning to see its environment, not just on Earth, but in space, and to take responsibility for its own survival against one of nature's most dramatic threats. Among the many asteroids that astronomers have discovered and tracked, one has become almost legendary in the story of planetary defense: Apophis. The tale of Apophis is often told as a harrowing near miss that taught us invaluable lessons. This asteroid's journey, from the moment of its discovery to the tense weeks of uncertainty, and finally to the confident tracking we have today, encapsulates the importance of our early warning efforts and the global cooperation behind them. Discovered in June 2004 by astronomers at the Kitt Peak National Observatory in Arizona, Apophis immediately drew attention. Initial calculations sent a shiver through the scientific community. This asteroid, about 370 meters across, appeared to have a disturbingly high chance of colliding with Earth on April 13, 2029. Early estimates gave about a 2.7% probability, which may sound small, but in asteroid terms, it was astonishingly high. For context, anything above a fraction of a percent is enough to raise alarms, and this was nearly 3 in 100. Apophis quickly shot to the top of risk lists and achieved the highest ranking ever seen on the Torino scale of impact hazard at that time. On the 0 to 10 Torino scale, where 0 means no risk and 10 means certain global catastrophe, Apophis was rated a level 4 during those early days. It was the first asteroid ever to reach that level. Level 4 indicates a close encounter meriting attention by astronomers and perhaps some public awareness, as it suggests a likely close approach with 1% or greater chance of a collision capable of regional devastation. In plain terms, there was a 1 in 37 chance that Apophis could hit Earth on that spring day in 2029. No asteroid of that size had ever been known to pose such a significant risk in modern times, and the news made headlines worldwide. For a few unnerving days in December 2004, people contemplated what an impact from a 370-meter asteroid would mean. The energy release would be enormous, equivalent to billions of tons of TNT, more than enough to flatten a state or create devastating tsunamis if it struck the ocean. It's the kind of event expected only once in many millennia. And here was a date on the calendar, just 25 years away, with a non-negligible chance of it coming to pass. Unsurprisingly, Apophis was named after the Egyptian god of chaos and destruction. A fitting moniker under the circumstances. But the very fact we had advance notice was a testament to our improving detection abilities. Unlike the dinosaur-ending impact, or Tunguska, or other past events that arrived without warning, humanity now had a heads up. The challenge was what to do with it. Immediately, astronomers around the globe turned their telescopes toward Apophis. The initial discovery data was limited, making the orbit calculation uncertain. Each night, additional observations helped refine the asteroid's trajectory. With each new data point, the cone of possible paths in 2029 narrowed. Within a few days, scientists were relieved to find the probability of a 2029 impact dropping. It soon became clear that Apophis would not hit Earth in 2029. It would come very close, but would miss. This was a massive relief. However, the saga wasn't over. The 2029 close approach itself would bend Apophis's orbit, since Earth's gravity would tug on it during the flyby. Initially, there was concern that if the asteroid passed Earth at just the wrong distance, through a tiny region of space called a gravitational keyhole, that encounter could tweak its path such that Apophis might return on a collision course in 2036. Essentially, missing in 2029 could set up a hit in 2036 if it threaded that gravitational needle. Calculations showed that keyhole to be small, only a few hundred meters wide, but it couldn't be dismissed until we knew exactly how 2029 would play out. Thus, astronomers continued to track Apophis, not just in 2004, but in subsequent years, whenever it was observable, gradually improving their knowledge of its orbit and the odds of future impact. By 2006, further optical tracking had confidently ruled out the potential 2036 impact as well. Apophis would not pass through the dangerous keyhole in 2029. The immediate crises abated. The worst-case scenarios for 2029 and 2036 were off the table. Still, a sliver of uncertainty remained for the farther future. There was one more date that had lingered in calculations: 2068. A very small possibility persisted that Apophis could impact in that year, depending on subtle factors like slight pressure from sunlight, the Yarkovsky effect, nudging its orbit over decades. For years, this kept Apophis classified as a non-zero risk object, though the probability was extremely low. The definitive breakthrough came in March 2021, when Apophis passed relatively close to Earth, around 17 million kilometers away. Not a threat, but close enough for good observations. During that approach, powerful radar telescopes at NASA's Goldstone facility in California and the Green Bank Observatory in West Virginia were used to ping Apophis and get exquisitely precise measurements of its position and velocity. These radar observations dramatically shrank the uncertainties in Apophis's orbit. Finally, astronomers could say with confidence that Apophis posed no risk of impacting Earth for at least the next 100 years. In fact, on March 26, 2021, Apophis was formally removed from the risk list of hazardous asteroids. What had once been the poster child of potential asteroid disaster was now, essentially, just a scientific curiosity, a known and well-behaved neighbour in space that would not hit us in the foreseeable future. The sense of relief in the planetary defence community was palpable. Here was proof that with sustained observation and international cooperation, even alarming asteroid threats could be analysed and, in this case, shown to be false alarms. Apophis taught the world not only about the potential danger, but also about our ability to stare that danger down with physics and patience. Now, with the fear of impact lifted, Apophis has transformed from a harbinger of doom into an unprecedented scientific opportunity. On April 13th, 2029, this asteroid will pass extremely close to Earth, about 32,000 kilometers from the surface, well inside the orbit of geosynchronous satellites. For comparison, that distance is roughly only 5 Earth diameters away. It will be the closest approach by an asteroid of Apophis's size that humans have ever known about in advance. On that day, under the night sky in parts of Europe, Africa, and Asia, people will actually be able to see Apophis with the naked eye, a bright moving star slowly streaking across the heavens. What once was a source of fear may become a moment of shared wonder for humanity, as millions look up to witness a mountain-sized object glide silently by. It's a rare event in our lifetimes, essentially a front-row seat to a cosmic flyby, and scientists are gearing up to take full advantage of it. Well before 2029, plans have been laid to observe Apophis intensely during its flyby. Astronomers worldwide will coordinate through the International Asteroid Warning Network to time their observations. Virtually every large telescope that can be pointed at Apophis will be watching. Optical telescopes to study its rotation and surface properties, radar transmitters to image its shape and surface features down to meter-scale resolution, and even space-based observatories to catch details impossible to see from Earth's surface. It will be a scientific bonanza, a chance to closely study a sizable asteroid without the need to send a spacecraft all the way to the asteroid belt. And Apophis's close approach will serve as a natural experiment. Earth's gravity is expected to significantly perturb Apophis's spin and maybe even its structure slightly. Tidal forces during the flyby might induce asteroid quakes or landslides on its surface, shaking off boulders or dust that have rested undisturbed for eons. If that happens, telescopes could potentially catch changes in Apophis's brightness or spectra that indicate surface disturbance. For scientists, it's a chance to see how a near-Earth asteroid responds to a close encounter, knowledge that could be very useful if we ever need to deliberately tug or deflect an asteroid ourselves. Moreover, both NASA and ESA are sending spacecraft to rendezvous with Apophis around the time of its Earth flyby, turning this event into a coordinated interplanetary mission of sorts. NASA has repurposed its OSIRIS-REx spacecraft, fresh off a mission returning samples from asteroid Bennu, to head for Apophis. Renamed OSIRIS-APEX for Apophis Explorer, the probe is expected to arrive at Apophis shortly after the 2029 close approach. Once there, OSIRIS-APEX will orbit the asteroid and even attempt a daring experiment, firing its rocket engines near Apophis's surface to kick up dust and small rocks. By observing the material that gets dislodged, scientists hope to peek beneath the weathered surface layer and learn about the asteroid's composition just below. It's a gentle way of touching the asteroid without blowing it up, essentially giving Apophis a little nudge to see what happens in the name of science. At the same time, ESA is planning a mission called RAMSES, Rapid Apophis Mission for Space Safety. RAMSES, if funded and launched in time, aims to rendezvous with Apophis during the flyby itself. It would travel alongside Apophis as it whips past Earth, observing in real time how Earth's gravity affects the asteroid's trajectory and structure. This would provide an unprecedented before and after comparison when combined with OSIRIS-APEX's later observations. Even if RAMSES doesn't launch, the very consideration of such a mission shows how Apophis's flyby is viewed as a crucial learning opportunity. The global excitement around Apophis is a testament to how far planetary defense has come. What could have been a doomsday scenario will instead be a well-studied close shave. The asteroid that once sparked fear will become, for a night, the most observed and perhaps the most celebrated space rock in history. And it offers a sort of dress rehearsal for handling potential threats. During Apophis's approach, international networks will simulate how they'd respond if it were actually on a collision course. They'll practice communication protocols, public outreach, and perhaps even consider how a deflection mission would have been executed if needed. All this without the existential pressure of a real impact looming, because thankfully Apophis will not hit us. In essence, Apophis allows humanity to get on the same page, or as ESA pithily puts it, on the same SMPAG, referring to the Space Mission Planning Advisory Group. SMPAG, pronounced same page, is an international forum of space agencies designed to coordinate any necessary asteroid deflection missions. The preparations for Apophis bring SMPAG's members together in a concrete way, strengthening the cooperative bonds and technical know-how that would be critical in a real emergency. Thus, the legacy of Apophis is largely positive. It energized the field of planetary defense at a crucial time. Back in 2004, it shocked policymakers and scientists into realizing that even mid-sized asteroids can appear out of the blue and present an alarming scenario. It likely influenced funding and support for surveys in the late 2000s and 2010s, accelerating the discovery rate of NEOs. It also demonstrated the effectiveness of global collaboration, with observatories from Australia to North America pitching in to observe Apophis, and NASA working with ESA and others to continually refine the risk assessments. Ultimately, it became a success story that showcases our growing capability to handle asteroid threats calmly and scientifically, where once the notion of an asteroid headed for Earth felt like inevitable doom. Apophis proved that knowledge truly is power. By knowing its orbit well, we turned a potential catastrophe into a manageable close encounter. Even the public's perspective on asteroids shifted with Apophis. Many people heard about the scary predictions in 2004, and then later heard that the danger was over. This wasn't by luck or miracle, it was through diligent observation and math. It's a subtle lesson in how science and preparation can demystify a threat from the heavens. And in 2029, when Apophis graces our skies harmlessly, it may inspire a new generation of stargazers and scientists. Some child peering up that night, marveling at the strange moving dot of light, might be inspired to become a planetary scientist or an astronaut, continuing the work of protecting Earth. The near miss of Apophis will live on in textbooks and documentaries, indeed, likely including this one, as a pivotal chapter in the story of how humanity confronted the asteroid danger and prevailed, not with explosions or heroics, but with cooperation, patience, and ingenuity. The story of Apophis naturally leads us to ask, what if one day we find an asteroid that isn't going to miss? Our detection methods might give us years of advance notice. What then? How do we move from watching and calculating to actually taking action? This question shifts our focus from early warnings to the next phase of planetary defense: deflection and diversion. If a sizable asteroid ever lines Earth up in its crosshairs, humanity will face the challenge of changing the asteroid's course. It's a daunting task, moving a mountain in space, but over the last few decades, scientists and engineers have been developing strategies to do exactly that. From the realm of science fiction, these ideas have steadily moved into the realm of practical experimentation. With a slightly mysterious calm, let us explore these strategies for deflecting danger and how we plan to play cosmic billiards with asteroids to protect our world. Imagine, in the quiet of space, a lonely asteroid tumbling end over end, millions of kilometers from Earth. Now imagine a bright speck appearing beside it, a spacecraft, purposefully sent to intercept this celestial wanderer. In humanity's toolkit for planetary defense, the kinetic impactor is perhaps the most straightforward concept. Simply put, hit the asteroid with something heavy enough and fast enough to shove it off course. It sounds almost childishly simple, like throwing a rock at a larger rock. But in the vacuum of space, a small nudge can go a long way. If done years in advance, a tiny change in an asteroid's velocity can add up to a big shift in its position by the time it would have reached Earth. For a long time, this idea remained untested, a theoretical solution awaiting proof. That proof finally came on a clear night in September 2022, when humanity, for the first time, altered the orbit of an asteroid moonlet on purpose. The mission was DART, Double Asteroid Redirection Test, a modestly sized spacecraft with a bold goal: to crash headlong into a small asteroid and see if we could measurably change its orbit. DART targeted Dimorphos, a moonlet about 160 meters wide that orbits a larger half-kilometer asteroid named Didymos. This target was chosen carefully. Dimorphos was not a threat to Earth, and orbiting within the Didymos system made it easier to measure any orbital changes. On September 26, 2022, After a 10-month journey in space, DART collided with Dimorphos at a speed of roughly 22,500 kilometers per hour. Back on Earth, telescopes and radar eagerly observed the aftermath. Days later came the remarkable confirmation. DART's impact successfully altered Dimorphos's orbital period around Didymos by a significant amount. Before the collision, Dimorphos took 11 hours, 55 minutes to circle its companion. After DART's cosmic punch, the orbit was shortened to 11 hours, 23 minutes. In other words, the little moonlet was now orbiting faster, evidence that it had moved closer to Didymos, exactly what would happen if DART's impact imparted momentum and gave Dimorphos a slight push. The change was about 32 minutes, far exceeding the mission's minimum success criteria of 73 seconds. This was a eureka moment for planetary defense. For the first time, humanity had deliberately altered the motion of a celestial object in a measurable way. What had been a concept in white papers was now real. The world watched the success of DART with fascination and not a little relief. If we can do that to a small asteroid moon, we can, in principle, do it to an asteroid headed for Earth, assuming we have enough warning and can mount a mission in time. NASA Administrator Bill Nelson hailed the mission as a watershed moment for planetary defense, demonstrating that we're no longer helpless in the face of a potential asteroid strike. The poetic irony was not lost. For eons, life on Earth has been at the mercy of wandering rocks in space. But now life, in the form of us, humans, had nudged one of those rocks onto a new path. It felt like a small but significant assertion of agency on a cosmic scale. In the details of the DART results, scientists found valuable lessons. The fact that the orbit change was so large, 32 minutes, hinted that the impact did more than just transfer the spacecraft's momentum. When DART slammed into Dimorphos, it blasted out a plume of debris from the asteroid's surface. This ejector acted like a jet of gas, providing additional thrust that magnified the deflection. It's akin to popping a balloon. The air rushing out pushes the balloon in the opposite direction. In Dimorphos's case, the rock and dust blown off by the impact gave it an extra kick. This effect turned out to be a very welcome bonus. It means a kinetic impactor can be even more effective if the asteroid is prone to spewing material upon impact, as many rubble pile asteroids likely are. Moving forward, understanding these physical details will help engineers design future impactors, their speed, angle of approach, even the possibility of multiple strikes, to maximize momentum transfer. Kinetic impact is a 1-2-step process in practice. Find the threatening asteroid early and hit it when it's far enough away to make a difference. The earlier the better. A tiny change in velocity, just a few millimeters per second, can accumulate over years to shift an asteroid's position by thousands of kilometers. So if we have, say, 10 or 20 years of warning, we don't need a very big impact to avert disaster. Conversely, if an asteroid were detected only months away from hitting Earth, a kinetic impact might not be feasible. There wouldn't be time to build the mission, or for the small velocity change to add up to a miss. In those frightening short-notice scenarios, other methods might be considered. But with sufficient lead time, sending one or more kinetic impactor probes remains a primary plan for deflection. Straightforward in concept, using proven rocket technology, and now validated by the DART experiment. It's worth noting that kinetic impact isn't about blowing up the asteroid. It's about giving it a controlled nudge. We don't want to shatter an asteroid, especially a large one, into many pieces that could still be on a collision path. The goal is simply to speed it up or slow it down by a tiny fraction, so that by the time it would have intersected Earth's orbit, it arrives either slightly earlier or later, enough that Earth has moved out of the way. In celestial mechanics terms, we change the asteroid's orbital period or energy just enough to miss the bullseye. This requires careful calculations and precision navigation to hit the asteroid at the right spot and angle. In DART's case, a target 160 meters wide was hit after a journey of 11 million kilometers. A remarkable feat of guidance. For future deflection missions, especially on potentially hazardous asteroids, similar precision would be required. But DART has given mission designers confidence that we can do it when needed. Another promising strategy is the gravity tractor, a more subtle and patient approach. Imagine a heavy spacecraft arriving at an asteroid and then simply hovering near it, maintaining a stable formation flight. In the vacuum of space, even a spacecraft's tiny gravitational pull can tug on the asteroid. Over months or years, this steady gravitational attraction can slowly alter the asteroid's path. It's like an invisible tow line, with gravity as the rope. The beauty of the gravity tractor method is that it is very controlled. There's no impact, no explosion, nothing that could break the asteroid apart. It works regardless of the asteroid's composition or spin. The downside, of course, is that it's slow and requires potentially a long time on station. For a gravity tractor to be effective, we'd likely need decades of lead time for a sizable asteroid, or we might employ it as a follow-up to a kinetic impact, fine-tuning the trajectory after the bigger push. NASA studied the gravity tractor concept in connection with a now-defunct mission idea called the Asteroid Redirect Mission, ARM. In that plan, a spacecraft would have plucked a boulder off an asteroid and then used that added mass to gravitationally tug the asteroid, demonstrating a deflection. While ARM was never flown, the concept showed that a spacecraft's own mass could indeed impart a gentle force. The principle is rooted firmly in Newton's law of gravitation. Any two masses attract each other, however faintly. A sufficiently massive spacecraft, or one that enhances its mass by grabbing a piece of the asteroid, could produce a measurable pull. This force would be minuscule, perhaps comparable to the weight of a sheet of paper. But in the frictionless environment of space, over time, that's enough to shift an asteroid's trajectory bit by bit. The key is station keeping. The spacecraft would need to maintain a steady position near the asteroid, likely using ion thrusters or other ultra-precise propulsion to counteract the gravitational pull and not simply drift into the asteroid. It's a delicate dance, a sort of celestial tug-of-war where the rope is gravity itself. One might picture it: a spacecraft silently hovering a few hundred meters from an asteroid's surface, thrusters occasionally puffing to adjust its position. There's no dramatic collision, no flash of light, just a steady, invisible hand guiding the asteroid. Over months, the asteroid's orbit shifts perhaps a few centimeters per day, barely noticeable at first, but cumulative over the years. By the time the asteroid would have intersected Earth's orbit, it might be tens of thousands of kilometers off target, missing Earth entirely. The gravity tractor method has the advantage of precision. It can also be turned off or on at will. If you overshoot, you could even position the spacecraft on the other side to tug the asteroid slightly back. It's the cosmic equivalent of a tugboat steering a large ship gradually away from a collision course. Though we haven't yet used a gravity tractor in practice, it remains one of the most elegant tools in the theoretical toolbox. One practical consideration is that it requires the spacecraft to rendezvous with the asteroid well before the predicted impact, meaning we need excellent tracking and prediction to know exactly where that asteroid will be and when, which circles back to early detection. It's all interlinked. Without early discovery, a method like gravity tractor can't be applied. But if we do catch a threatening asteroid decades ahead, a gravity tractor mission could be dispatched to gently shepherd the asteroid into a harmless orbit. And unlike a one-time impactor, a tractor spacecraft could adjust its strategy on the fly, making it a very flexible defense. Now, consider scenarios where time is short, or the asteroid is very large. We might not have the luxury of multiple gentle nudges. This is where a more extreme measure enters the discussion, the nuclear option. It's an approach often dramatized in movies, with notions of bombs drilling into asteroids and heroes sacrificing themselves. But the reality envisioned by planetary defense experts is quite different and more nuanced. The idea is not to blast the asteroid to smithereens. That could make things worse by creating many hazardous fragments unless done far, far in advance. Instead, the preferred concept is a standoff nuclear detonation, exploding a nuclear device at some distance from the asteroid, so that intense radiation and energy pulse against one side of the asteroid, vaporizing a thin layer of its surface. In that instant, the vaporized material expands rapidly outward as a hot plasma, and like a rocket exhaust, it imparts a thrust to the asteroid in the opposite direction. In the words of one physicist, it's essentially turning the asteroid into its own rocket for a brief moment. The asteroid's surface that is irradiated acts like fuel being ejected, pushing the remaining bulk of the asteroid onto a slightly different trajectory. This method is orders of magnitude more forceful than a kinetic impactor. While a kinetic impactor might change velocity by millimeters or centimeters per second, a properly executed nuclear standoff burst could impart a change of perhaps tens of centimeters per second or more, if needed. That's why it's considered a last resort for the largest asteroids, or when warning time is very short. If we detected a 1-kilometer asteroid only a year or two out, a nuclear approach might be the only thing with enough punch to do the job. It's a dramatic measure, but in the face of an existential threat, it could be humanity's best shot at survival. Scientists have been studying the nuclear deflection idea through simulations and even laboratory experiments. Physicists at Sandia National Laboratories, for instance, conducted detailed simulations and a physical experiment with laser-driven X-rays to understand how an intense burst of radiation would affect an asteroid's material. Their research demonstrated that indeed, a properly timed nuclear detonation could vaporize a layer of an asteroid's surface and provide a significant shove without pulverizing the whole rock into fragments. The key is standoff distance. You don't want to hit the asteroid directly with the bomb, like a bomb hitting a bunker. Instead, you detonate perhaps tens to hundreds of meters away, bathing the surface in heat and neutron radiation for a few microseconds. Done correctly, this would avoid blowing the asteroid apart. It would only ablate its surface. The expelled mass does the pushing. Calculations suggest this strategy could work even for asteroids a few kilometers wide, given enough explosive yield, and it scales up. Bigger bomb, more push for even larger asteroids. There isn't a strict upper limit. It's more about how much warning time and how large of a device one can practically deliver. Of course, using nuclear explosives in space raises weighty issues. There are international treaties to consider. The Outerspace Treaty prohibits nuclear weapons in orbit or on celestial bodies, though intercepting an asteroid might be argued as an exception in an emergency. There are political concerns. Who decides to launch a nuclear device and who provides it? Such a mission, if ever needed, would likely require unprecedented international collaboration and trust. Yet, in a crisis, one imagines that these hurdles would be overcome. If the alternative were global catastrophe, nations would likely unite to take the necessary action. It's heartening that when scientists discuss this option, it's not with cavalier enthusiasm, but with sober caution. They call it the method of last resort, to be contemplated only when other methods can't do the job. As Professor Gareth Collins, a planetary scientist, noted, "I still have a strong preference for non-nuclear options, but for a very large asteroid or a short warning time, this type of approach may be our only option. It's the safety net beneath the safety net, and we hope never to need it." There's also ongoing research into more exotic or less mature deflection methods. One idea is laser ablation, stationing either a powerful laser on a spacecraft near the asteroid or even on Earth for nearer asteroids, to focus energy on the surface of the asteroid. By heating the surface to high temperatures, bits of rock would vaporize and again create a jet-like plume, nudging the asteroid slightly. This concept requires advances in laser technology and enormous energy, but in theory could allow a continuous gentle push from afar. Another concept is deploying solar concentrators, essentially giant mirrors or lenses, to concentrate sunlight onto an asteroid's surface, achieving a similar ablation effect using the sun's power. Yet another idea is mass drivers, landing a device on the asteroid that scoops up regolith, surface material, and throws it off into space at high speed. Each launched scoop would recoil the device, and thus the asteroid a bit in the opposite direction, like a person slowly propelling a raft by throwing boulders off it. Such a device could run on solar power and operate for months to effect a change. And then there are more fanciful notions like painting an asteroid to change its reflectivity and thus alter the slight pressure sunlight exerts on it over time, the Yarkovsky effect. A darker or lighter surface will heat differently in sunlight and re-radiate heat in a way that imparts a tiny force. Over many years, this could shift an orbit. It's a very subtle and slow influence, likely impractical for timely deflection, but it underscores the creativity at play. All these methods share one common thread. They must be deployed well before the asteroid would hit. None of them, except possibly a nuclear blast, can help if we only find the asteroid days or weeks out. In that grim scenario, the options shrink to near zero, perhaps evacuating the projected impact zone if possible, and hoping for the best. Fortunately, our expanding detection network is aimed at preventing such late surprises. The whole purpose of early warnings is to enable these deflection strategies to be used. And as we've seen, those warnings are improving. The difference between a panic with no options and a solvable problem is often just a matter of time. One comforting fact is that the physics of orbital motion gives us multiple chances with many asteroids. If we miss the chance to deflect on one pass, often the asteroid would orbit the Sun and come back years later. Even being able to shift it slightly on a subsequent orbit could avert the impact. Earth is a small target in the vastness of space. A deflection does not need to move an asteroid by much to make it miss us, because space has far more empty room than occupied planet. So any of these methods, if executed even moderately well, should suffice, as long as we apply them in time. So we have at our disposal brute force kinetic strikes, subtle gravitational tugs, and the extreme push of nuclear blasts, among others. It's a rather impressive armory for a species that only a century ago didn't even know asteroids could be an existential threat. We have, in essence, begun to figure out how to play cosmic billiards, gently nudging celestial balls so they don't sink into the Earth pocket. It's an ongoing learning process. Missions like DART are our first practical lessons. Upcoming missions like ESA's Hera, which will visit Dimorphos to survey the post-impact crater and measure DART's effects precisely, will be the next. Each test makes us more prepared. Perhaps in the future, space agencies will conduct more ambitious trials, maybe even deflect a non-threatening asteroid in interplanetary space, just for practice. While that isn't on any official roadmap yet, it's conceivable as international cooperation grows in this arena. All of these efforts, detection and deflection, lead to one ultimate goal: protecting our Earth. It's often said that asteroid impacts are the most preventable natural disaster. Unlike earthquakes or hurricanes, which we cannot stop, only evacuate and shelter from, an asteroid impact is something we could actually avert entirely if we know it's coming. That notion is profoundly encouraging. It means our fate isn't solely at the mercy of the cosmos. We have some say in the matter. However, that empowerment comes with a responsibility. We must stay vigilant and proactive. We are in a race, in a sense. A race to discover and catalogue asteroids faster than new ones, from our perspective, approach us. A race to develop deflection capabilities before we truly need them in an emergency. And if an emergency comes, a race against the celestial clock to deploy a solution in time. It's a quiet race, without much fanfare in daily life, but the stakes are literally sky high. In recent times, humanity has been testing this whole planetary defense system in drills and even minor real events. Early 2025 brought a perfect example of how the process might play out. Late in December 2024, an automated telescope in Chile, part of the Atlas network, discovered a new asteroid, later designated 2024 YR4. It was about 100 meters in diameter, a size that could cause immense damage if it struck Earth. Within days of discovery, orbital calculations indicated something disconcerting. This asteroid had roughly a 1% chance of impacting Earth in the year 2032. In fact, it was quickly rated Torino Scale 3, the most notable threat since Apophis's early ranking. A Torino 3 means a close encounter with a probability of impact, perhaps a few decades out, warranting attention by astronomers and a bit of public notice. This wasn't a guaranteed disaster by any stretch. There was a 99% chance it would miss Earth entirely, but a 1% chance of a major impact is enough to set plans in motion. And indeed, for the first time, the formal global planetary defense apparatus was activated on a significant scale. The International Asteroid Warning Network sent out notifications urging observatories worldwide to observe 2024 YR4 to refine its orbit. Telescopes from Europe to North America to Asia joined in the campaign, trying to pin down the asteroid's trajectory. At the same time, the Space Mission Planning Advisory Group, SMPAG, was alerted. This meant experts from multiple space agencies began quietly discussing what options we'd have if further observations kept that 1% risk, or worse. They'd consider scenarios like, if in a few years it still looks like an impact probability remains significant, should we prepare a deflection mission? Perhaps a kinetic impactor to launch by, say, 2028, to nudge it well before 2032. These discussions, though not public at the time, were a real exercise of exactly the machinery built after years of planning. It was humanity's planetary defense playbook being opened to the first chapter. For several weeks, astronomers tracked YR4 as much as possible. Initial data had a challenge. Soon after discovery, the asteroid was headed away from Earth, nearly in a straight line, making it hard to get good angle measurements on its orbit. There was a chance we'd lose sight of it until it came closer years later. But fortunately, enough observations were gathered by late January and early February 2025 to greatly reduce uncertainties. As the data poured in, each refinement of the orbit saw that ominous 1% chance dwindle. By late February, the calculations showed essentially zero probability of a 2032 impact. The asteroid would, as most do, pass harmlessly by. The alerts were stood down. IAWN sent out a final notice that 2024 YR4 posed no significant danger. The world at large hardly noticed that we had a potential scare. Maybe a few news articles like the Guardian piece noting the initial risk and subsequent relief. For those inside the process, it was a gratifying outcome. The system worked exactly as designed. A threat was detected, assessed, watched, and then cleared. We essentially had a fire drill for an asteroid emergency, and we passed. This episode illustrates how humanity's plans to protect the Earth are not just theoretical, They are operational and active right now. We have an organized global response ready to go when needed. There are people whose job titles literally involve planetary defense officer, like Lindley Johnson at NASA, or analogous roles at ESA and other agencies, who wake up each day thinking about how to improve our readiness for the next asteroid threat. When a new asteroid is discovered, automated systems immediately cross-check whether it could hit Earth. NASA's Sentry system and ESA's Clomon system continuously scan known asteroid orbits, predicting years into the future, looking for potential impacts. If any are found, they pop onto risk lists, like NASA's online Sentry risk table or ESA's risk list, where they're monitored. Most often, as new observations come in, they get removed from the list, just like Apophis and YR4. Our knowledge erases the risk. In rarer cases, if something were to stubbornly stay risky, that's when the gears of mission planning would truly grind into motion. So far, we haven't had to launch a deflection campaign in a real emergency. It's a milestone we hope never to reach. But if we do, the groundwork is laid. There are international agreements in place that any significant threat will be communicated through the United Nations framework, ensuring all nations are informed. The UN's Committee on the Peaceful Uses of Outer Space has endorsed the work of IAWN and SMPAG to handle the info sharing and decision support aspects. In 2019, for instance, at a planetary defense conference, an academic meeting held every 2 years, participants ran a week-long exercise simulating an incoming asteroid scenario. They practiced what advice they'd give to political leaders, how they'd choose between options like evacuation or deflection, how they'd handle the uncertainties in public messaging. These kinds of rehearsals are invaluable because an actual impact threat could be as much a social challenge as a technical one. Avoiding panic, deciding on evacuations, etc., all under potentially severe time pressure. One often cited success in building public awareness is Asteroid Day, observed each year on June 30th, the anniversary of the Tunguska impact in 1908. This UN-recognized day encourages education and activities around asteroids and planetary defense. It's part of making sure the public isn't taken by surprise or filled with misinformation should a real threat emerge. The more people understand that we have a plan and capabilities, the less fear there will be if we ever have to implement them. It transforms the narrative from one of helpless apocalypse to one of challenge and response. We've gone from the 1990s, when asteroid impact was mostly the fodder of blockbuster movies, to the 2020s, where schoolchildren can tell you about DART, and scientists regularly speak on news programs about asteroid preparation with calm authority. Another aspect of our planetary defense plan is future technology development. While we have solid ideas now, research continues into making them better. For example, if we ever needed a nuclear standoff mission, understanding exactly how to optimize the neutron output or X-ray output of the device to maximize surface ablation is an ongoing research area. Developing space nuclear propulsion might help us reach asteroids faster if time is short. In non-nuclear realms, more powerful launch vehicles, like NASA's SLS or SpaceX's Starship, could enable delivering larger impactor masses or multiple spacecraft in one go to an asteroid. Some scientists have proposed swarm strategies, sending a fleet of small impactors that hit sequentially like a rapid-fire punch. As private spaceflight advances, perhaps even commercial rockets could be called upon to loft emergency interceptors on short notice if needed. We are essentially arming the Earth with knowledge and tools, hoping we'll never need to fire those tools in anger, but practicing nonetheless. Notably, planetary defense is an endeavor that unites countries rather than divides them. The threat of an asteroid impact doesn't discriminate by nation. it's a global problem. This has led to a rather harmonious international community of experts. American, European, Russian, Chinese, Indian, Japanese, and other scientists regularly collaborate on research papers about impact mitigation. Missions like DART had international contributions. The Italian Space Agency provided a tiny companion spacecraft, Lycia Cube, that photographed the impact. ESA's upcoming HERA mission involves collaboration with American astronomers to interpret results. The more we prepare, the more we find common cause across borders. One could say the asteroids are unknowingly fostering a bit of global unity. After all, if someday we have to make a decision to, say, use a nuclear device in space, it would likely be a joint decision by world powers, executed collectively. The scenario almost necessitates a level of cooperation rarely seen, except perhaps in climate change efforts or large science projects like the International Space Station. As of now, we can look at the risk list of known asteroids and be reasonably assured that we're safe for the next century from any civilization-ending impact. The few asteroids that do have a minute chance of impact decades from now, such as a half-kilometre asteroid Bennu, which has a tiny probability of hitting Earth in the late 2100s, are being actively studied. In Bennu's case, we even sent OSIRIS-REx there to collect samples, learning more about its composition and orbit to better calculate its future trajectory. The knowledge we gain from these close studies reduces the uncertainties further, usually diminishing the hazard probability. Bennu's impact chance is something like 1 in 2,700 in the year 2182. Not zero, but extremely low, and we have a long time to watch it. With continued observations, that too will likely be ruled out. Or if not, our descendants a century from now will have plenty of time to prepare a deflection if needed. Standing here in the mid-2020s, one gets the sense that we're in a pivotal period. We have finally identified most of the really big threats. We have tested our first deflection technology, and we have frameworks in place to respond to a looming impact. It's as if we've built a fire station and trained a crew, though the fire we fear may not come in our lifetimes, and we dearly hope it doesn't. Yet, there is no complacency. The mantra in this field is keep looking, keep planning. New telescopes, like the Vera C. Rubin Observatory, coming online in Chile with its ultra-sensitive survey camera, will soon start discovering enormous numbers of asteroids, perhaps tens of thousands of new ones each year, including many NEOs. That will further fill in the map of our inner solar system. Missions in planning, like maybe a next-generation follow-on to DART that could test deflection on a different type of asteroid, are being discussed. The planetary defense community is continually refining their response plans, learning from events like the Chelyabinsk meteor on how to communicate with the public and handle surprise small impacts. While all these preparations continue, the general public mostly goes about life without worrying about asteroids day to day. And that's how it should be. These are low-probability events. But it's reassuring to know that in quiet rooms and observatories around the world, dedicated teams are worrying about asteroids on our behalf, or rather, thinking about them proactively so the rest of us don't have to lose sleep. They carry a slightly mysterious calm about them, those asteroid guardians, perhaps because they spend so much time contemplating cosmic dangers that perspective becomes second nature. They can talk about a potential impact in 2032 or 2182 with the same measured tone one might discuss insurance, acknowledging the risk, but focused on mitigation and solutions. In a sense, this all represents humanity growing up as a spacefaring civilization. We are learning to protect ourselves not just from terrors of our own making, but from external natural disasters that once were beyond any control. It wasn't long ago, in geological or even historical terms, that an asteroid ended the age of the dinosaurs. If one imagines, poetically, the spirits of those ancient creatures looking on, perhaps they'd nod in approval that their successors, tiny mammals that evolved into toolmakers, have figured out how to spot the next big rock coming and push it away. The Earth has been hit many times in its history, but now, for the first time, one species has the knowledge to say, not this time. It's a profound shift. The cosmos hasn't changed, but our relationship to it has. We're no longer passive inhabitants. We're becoming active guardians of our planet. And yet, despite all our plans, one can never eliminate every bit of uncertainty. The universe has a way of surprising us. What if tomorrow, an undiscovered comet from the outer solar system appeared on a collision trajectory? Comets, unlike asteroids, can sometimes come barreling in with only months of notice, since they spend most of their time far from the sun's light. The planetary defense community has thought about that too. Though rare, it's a scenario that worries them because our surveys aren't as comprehensive for long-period comets. In such a case, deflection might be nearly impossible if the warning is too short. The world would have to focus on disaster response and perhaps a nuclear attempt as a break-glass measure. It's a reminder that even as we get better, we'll never have zero risk. There's always a background chance, however small, that the cosmic lottery hands us a challenging ticket. What then would we do in that ultimate worst-case scenario, when an impact is certain and imminent, despite everything? That brings us to the final part of our journey. We have seen how we find asteroids, how we learned from Apophis, and how we might deflect one given time. Now, we turn to the situation where time has nearly run out, and humanity must face a falling sky. How would the world react in those final weeks and days? What plans exist to shelter civilization from a blow we failed to divert? As we continue, we delve into those somber yet compelling questions, racing against time not just to plan, but to survive and recover if the unthinkable happens. In the silent void of space, a massive asteroid drifts through darkness. It is a lonely wanderer of the cosmos, an irregular chunk of rock and metal scarred by eons of minor collisions. Stretching several kilometers across and weighing billions of tons, this asteroid is truly a mountain adrift in the heavens. On its pitted surface, ancient craters and dusty plains testify to its long journey through the solar system. For millennia, it has wandered the darkness, cold and alone, an ancient remnant of creation that has seen worlds form and pass away. Now, fate guides this enormous mass on a path toward Earth. Without sound or warning, it hurtles ever closer to the blue planet, drawn in by Earth's gravity, toward an inevitable meeting that has been millions of years in the making. Far below on Earth, a seemingly ordinary day and night unfold in ignorance of the impending disaster. Half of the planet basks in daylight, where oceans sparkle under the morning sun, and people go about their daily routines. The other half lies in darkness, where continents sleep beneath calm, starlit skies, and nocturnal creatures quietly roam. All around the globe, life proceeds as usual. Cities hum with late-night activity or early morning work, and countryside villages rest in tranquil slumber. No one at this moment perceives the colossal threat racing toward them from above, a danger about to shatter the planet's peace. High above, the asteroid finally reaches the edge of Earth's atmosphere. an invisible boundary between space and air. In that instant, everything begins to change. Moving at over 20 kilometers per second, many times faster than a rifle bullet, the asteroid slams into the thin upper air. The first contact is violent. Sparse atmospheric molecules that barely exist at the threshold suddenly collide with the asteroid's face, generating intense heat. Air compressed in front of the hurtling rock glows in a sudden burst of light, and a faint orange glow appears around the asteroid's leading edge. What was once a silent, frozen traveler is now instantly wreathed in fire. Thin gases that had been harmlessly floating at the edge of space ignite into plasma as the colossal object plows deeper. The asteroid plunges further down, compressing the air before it so fiercely that the air itself burns white hot. A brilliant streak of light now tears across the sky, announcing the visitor's arrival to the world below with a fiery herald. What was once a silent, frozen traveler is now instantly wreathed in fire. Thin gases that had been harmlessly floating at the edge of space ignite into plasma as the colossal object plows deeper. The asteroid plunges further down, compressing the air before it so fiercely that the air itself burns white hot. A brilliant streak of light now tears across the sky, announcing the visitor's arrival to the world below with a fiery herald. On the ground, the calm of night is suddenly broken by this uninvited light. People who had been anxiously awaiting this moment now see their fears made real. A searing point of light has appeared high in the sky. In mere heartbeats, it swells from a tiny star-like speck to a furious, blinding ball of fire. For those watching in the pre-dawn darkness, it is as if a second sun is rising, casting stark new shadows and bathing the landscape in an otherworldly glow. Observers, hundreds of miles away, stop in their tracks as the heavens light up without warning. Windows and walls begin to shiver faintly as a deep, low rumble rolls in from above. A distant thunder, heralding the chaos that is about to unfold. As the asteroid descends deeper into the atmosphere, it drags a churning tail of fire and smoke behind it. Molten fragments of its outer layers are stripped away by the fierce friction and blown out in a glowing trail, sparkling like a cascade of fiery stars in its wake. The sky itself appears to burn around the speeding intruder. From horizon to horizon, a luminous streak etches itself across the heavens, momentarily outshining the moon and even challenging the brilliance of the sun. Birds roosting in trees awaken and scatter in confusion at the sudden false dawn. Nocturnal animals scramble back to their burrows, sensing in their primal brains the enormous danger blazing above. In towns and cities, dogs howl and bark at the sky, and people gape upward in terror and wonder as the fiery streak illuminates the world below. Higher and higher the temperature climbs around the plunging asteroid. Within seconds, its surface is heated to thousands of degrees. Metals and minerals on its exterior liquefy and boil off, adding ever more fuel to the incandescent tail streaming behind. The immense pressure of ploughing through the thickening air begins to deform the asteroid's shape. It remains largely intact, a colossal molten core wrapped in flames, but it quakes and shudders as pieces of its outer crust crack away. A shockwave forms in the air ahead of it, peeling off and trailing along its sides. It is like a glowing spear thrusting through the atmosphere, unstoppable and ferociously hot. The sky itself roars in protest as the asteroid forces its way down at a speed beyond anything the world has ever seen. Barely a handful of moments have passed since the asteroid first grazed the atmosphere, and already it is screaming through the skies over Earth's inhabited lands. Below it, Entire regions lie under its blazing path. The fireball now dominates the sky, casting a harsh, flickering glow over mountains, forests, and cities alike. Night is erased in its passing, turned into an uncanny imitation of daylight. Many onlookers find themselves frozen in place, awestruck and terrified by the sight overhead. Others, gripped by panic, rush for any shelter they can find, hearts pounding with each step. They know, deep down, that no ordinary shelter can protect them from what is coming. Yet the instinct to seek cover takes hold. In streets and fields, some people drop to their knees or embrace loved ones tightly, uncertain if these are their last moments. The world below holds its breath, collectively bracing for the inevitable. All the while, a continuous thunderclap accompanies the descending fireball, the shockwave of its passage moving just behind it. This cone of superheated, compressed air crashes downwards, rattling buildings and sending tremors through the ground. Windows shudder, and some even shatter from the pressure as the sonic boom sweeps over communities beneath the trajectory. In the final miles of its descent, the asteroid's brightness intensifies to a degree unimaginable, rivaling the very heart of the sun. Clouds in its direct path vaporize into wisps of steam, erased by the extreme heat in an instant. The sky below turns an eerie blue-white, illuminated by the searing glow. Shadows on the ground sharpen and stretch as this unearthly light intensifies. In the asteroid's wake, a churning trail of glowing vapor and smoke briefly marks its passage across the sky, leaving a transient scar of light above. In these final seconds, time itself seems to slow to a crawl. The asteroid, now a furious bolide encased in brilliant flame, hurtles toward its final destination. The ground races up to meet it, an expanse of coastal plain and the adjoining shallow sea directly in its path. At the impact point, the early morning is quiet and still. Gentle waves lap the shore, and a golden glow of dawn is just peeking over the horizon. In a nearby harbour, fishermen pause at the strange light in the sky, unaware that they have only seconds left. Birds that were beginning their morning chorus continue to sing, oblivious to the fireball about to strike. The final heartbeats tick by in silence from the ground's perspective. The asteroid's deafening roar has still not caught up to it. Then, in a single blinding pulse of light, the asteroid meets the Earth. An impact that has been building over eons happens in less than a heartbeat. The massive rock strikes with an explosive power beyond human experience. More energy released in one instant than if millions of the world's strongest bombs had detonated together. In that split second, the asteroid is no more. It is transformed into a ball of superheated vapor and molten fragments, and the ground itself seems to splash and erupt like an ocean wave under the tremendous energy of the impact. A searing fireball blooms at the point of impact, brighter than 1,000 suns. For a brief moment, night is banished across a huge swath of the world in a blinding flash that can be seen far, far away. In the immediate vicinity, darkness turns to light, as if an enormous camera flash has gone off. Anyone unfortunate enough to be nearby and looking toward the impact is instantly blinded by the intensity. The energy of the collision is so immense that it ignites the very air itself into a burning plasma. A furious wave of heat radiates outward from ground zero in those first seconds, heat hotter than the surface of the sun, incinerating everything in its immediate reach. Within a radius of several tens of miles, the heat is so extreme that the ground is scorched black, and every living thing is either vaporized or turned to charred husks in an instant. The ground buckles and vaporizes where the asteroid strikes. Solid rock turns to fluid under the colossal pressures. Bedrock flows like water, blasted outward from the impact point in every direction. Within seconds, a vast crater begins to gouge its way into the earth, a gigantic hollow in the crust that grows wider and deeper by the moment. It will soon stretch tens of miles across and several miles deep, a scar of unimaginable size. Anything at the impact site, soil, rock, water, or living, has been utterly obliterated, consumed in the fire and shock of the explosion. For a brief moment, the very earth behaves like liquid under the force. The crust rebounds and ripples, sending waves of rock surging outward. A central peak of molten earth rises up in the middle of the new crater, only to collapse back on itself. Seismic shockwaves penetrate deep into the ground, radiating outward as a devastating earthquake, far greater than any ever recorded. The planet shudders from the blow, and the surrounding terrain is torn apart by the violent shaking. Almost immediately, a towering plume of debris erupts upward from the impact site, punching through the atmosphere with explosive force. It forms a colossal pillar of fire and ash, carrying vaporized rock and fragments of the asteroid high into the sky, even toward the edge of space. Within this boiling column, everything is chaos. Fragments of Earth and asteroid swirl together, heated until they glow white-hot amid the roiling fireball. The mushroom-shaped cloud balloons outward as it rises, reaching the stratosphere within a minute and still climbing. Sparks of lightning crackle through the cloud's billowing stem and cap as static charges build in the turbulent mix of dust and vapor. For anyone watching from afar, this cloud becomes the most terrifying sight on the horizon, a boiling dark plume marking the impact for hundreds of miles. It is as if a volcano as tall as the sky has been born in an instant, and its mushrooming summit casts a pall of darkness over the surrounding land. At ground zero itself, nothing remains of the world that was there before, only a gaping, raw crater. The crater's edges are already starting to crumble and collapse inward, landslides of molten and pulverized rock tumbling down its walls. The enormous cavity continues to widen and deepen with each passing moment as the ground settles. Beyond the crater rim, for dozens upon dozens of miles in every direction, the landscape has been effectively wiped clean. Any forests that once stood are gone without a trace, reduced to ash and embers. Any city or town nearby has been utterly erased, buildings blasted to dust and foundations swept bare. The blast has literally stripped the topsoil off the ground, scouring the surface like a cosmic broom. All that remains is a blasted, barren plain of smouldering cratered earth, stretching out from ground zero. The thermal radiation unleashed by the impact sparks blazes far beyond the immediate blast zone. Within moments, an immense ring of wildfire ignites around the impact area. For hundreds of miles in every direction, exposed dry grass, forests, and structures burst into flame under the onslaught of heat. A split second after the flash, wooden buildings and trees as far away as the horizon are set alight, as if struck by invisible flame. Even people and animals at those distances are not spared. Any exposed skin is scorched, and many collapse where they stand, overcome by the sudden searing heat. In an instant, a vast circle of the earth is burning. Countless separate fires merge into an expanding inferno, a halo of fire surrounding the impact site almost as soon as the light from the blast fades. Thick smoke begins to rise from all directions, feeding into the darkening sky. Only after the light and heat does the sound of the cataclysm arrive. A few beats after impact, a deafening, sky-shattering boom crashes across the land. The delayed concussion erupts with a roar that seems to split the very air, a cacophony as if the atmosphere itself has exploded. This is the sound of the shockwave, now rushing outward from ground zero. It slams into everything in its path with unimaginable force. Hurricane winds, multiplied dozens of times beyond any storm ever known, tear across the blasted region. Near the impact, the wall of air and debris moves faster than a jet plane, a scorching hurricane of rubble and flame that scours the ground. These winds likely exceed 1,000 kilometers per hour, pulverizing anything that might somehow have remained standing. The shock front races outward, flattening everything in its widening path. Entire forests beyond the immediate blast zone are leveled in an eye blink, trees snapped like twigs and sent flying through the air. Any remaining structures, no matter how sturdy, are demolished, walls blown down, steel frames twisted and toppled. Debris is hurled ahead of the blast wave like shrapnel, battering everything further out. The very ground is swept clean by the force. Soil, rocks, and debris are picked up and carried on the howling winds. For dozens of miles from the impact, absolutely nothing remains standing or intact. Even farther out, 100 or more miles away, the shockwave still has strength. It knocks people off their feet, shatters windows in distant cities, and rattles buildings hundreds of miles from the blast. The thunderous boom rolls on, echoing across mountain ranges and plains. It will be heard around the world, the pressure waves circling the globe multiple times before fading. Where the asteroid struck the ocean's edge, the devastation extends from land to sea. In the shallow waters near the impact, the blow vaporizes millions of tons of water instantly, and then pushes what remains outward with explosive force. For a moment, the sea near the impact is blasted away entirely, the seafloor laid bare and steaming before the water crashes back in. A colossal wave rises from that chaos, thousands of feet high at the start. This towering tsunami radiates outward from the impact zone, churning the ocean. The first wall of water surges toward all nearby coasts at jet-like speeds. Coastal areas, tens to hundreds of miles away, will be struck within minutes by a flood of unimaginable height, bulldozing its way inland. Ships are tossed aside like toys, and shorelines are utterly reworked in an instant. Even far across the ocean, hours later, the impact's fury will be felt, as series of large waves roll up on distant shores, carrying remnants of destroyed ports and sea life, the last echoes of the cataclysm in the sea. Back at the impact site, after the initial blast passes, a strange and momentary silence falls. In the immediate aftermath, the air has been blown outward, leaving a brief vacuum of sound in the center of the destruction. For a few eerie seconds, there is a lull, as if the world is too stunned to make a noise. Then the calamity resumes its course. The vacuum is filled as winds rush back in, and the noises of an annihilated landscape begin. Flames that were sparked by the impact now roar to life all around. Those countless fires, fed by dry fuel and oxygen drawn in by the rising heat, coalesce into a massive firestorm. Superheated winds feed the inferno, fanning it into a continuous sea of flame that sweeps over the rubble. Whirlwinds of fire dance in the burning wasteland, tornado-like fire columns spawned by the intense heat and turbulence. The very air becomes unbreathable, consumed by the flames and filled with smoke and ash. The core of the blast zone, already flattened, is now engulfed in an ocean of fire stretching outwards, turning the devastated land into a furnace. High above, the gigantic column of dust and debris from the impact continues billowing into the heavens. It has pierced the atmosphere and spread out into a vast mushroom cloud that spans the sky. Billions of tons of Earth and asteroid have been lofted upward, forming a canopy of dust that is beginning to wrap around the planet. Within this cloud, debris of all sizes is being cast out on ballistic paths. Molten droplets of rock cool into glassy beads as they fly through the upper atmosphere. Larger chunks of rock, some the size of boulders or even houses, are hurled beyond the horizon. A few pieces are thrown so hard that they escape Earth's gravity for a time, arcing through space before gravity pulls them back. But the vast majority of this ejected material will rain back down. Over the coming minutes and hours, the sky will unleash a deadly fallout of debris across the world. Some of it starts to fall relatively nearby, pelting the surrounding regions with red-hot rocks and igniting more fires. Much more will travel high above the clouds and eventually descend far away, ensuring that no region is truly safe from the impact's reach. In the immediate blast radius, stretching for dozens of miles from ground zero, there is little chance of survival for any living thing. But even far beyond that zone of total destruction, the catastrophe is only beginning. Those who survived the initial shock in outlying areas will soon face new horrors. Choking smoke, falling debris, poisoned skies, and the collapse of their world as they knew it. The first minutes have delivered unimaginable devastation locally, yet the aftermath will spread the disaster to every corner of the globe. Even now, the shock waves and heat are dissipating into the distance, still capable of causing damage hundreds or thousands of miles away. Seismic tremors from the impact are propagating through Earth's crust, and the atmosphere is carrying the roar and energy around the planet. As the dust begins to settle over the blasted landscape, an apocalyptic scene is revealed. The ground for miles is glowing and smoking, littered with charred remnants. The sky, filled with roiling black clouds of ash, has turned the early daylight into a dim orange twilight. And yet, for all this destruction, it is only the first act of the catastrophe. The true scale of the impact's consequences is about to unfold in the hours and days ahead, transforming the entire world. No part of the Earth will escape the effects of this moment, a disaster that will soon envelop the globe in its aftermath. Above the Earth, the gigantic plume of ejecta from the impact continues to billow outward, having burst through the upper atmosphere. It expands like a vast umbrella of ash and rock, spreading around the globe at incredible speed. Within minutes, this plume begins to encircle the planet, a ring of debris high in the sky. Not long after the blast, incandescent material that was hurled into space now starts to fall back towards Earth. From all directions, a meteoric rain commences, countless glowing fragments streaking through the atmosphere as gravity pulls them home. These are pieces of Earth and asteroid that have been lofted around the world, now returning as fiery projectiles. These falling embers mark the beginning of a second phase of destruction, a global firestorm. As the debris re-enters the atmosphere, each fragment becomes a tiny meteor, blazing with heat. The skies far from the impact, even on the opposite side of the world, come alive with what looks like a shower of shooting stars. But these stars bring calamity, not wonder. Each incandescent piece of rock and ash transfers its heat to the surrounding air as it streaks downward. Soon, the entire sky grows hot, as if turned into a giant broiler. The intense infrared heat from above beats down on the surface. Dry leaves, fields, and forests that were spared the initial flames now wither and ignite under this sudden oven-like heat from the heavens. Even cities far removed from the blast find their rooftops and treetops growing warm, then hot, then spontaneously catching fire as glowing debris rains down upon them. All around the world, wildfires erupt almost at the same time. In remote woodlands, Thousands of miles from the impact, an eerie glow rises as whole forests are set alight under the blazing sky. In grasslands and jungles, dry scrub and canopy foliage burst into flames as if a giant invisible sun lamp were shining on them. In cities an ocean away from ground zero, people stare in disbelief as distant horizons flicker orange and smoke begins to curl up from roofs and hills. Places that once felt safe, simply by virtue of being on the opposite side of the planet, now confront a new horror: fire raining from above. Sparks and fragments ignite whatever they touch. The smell of smoke becomes universal. The initial impact may have been far away, but its effects are now literally falling out of the sky everywhere. By a few hours after the impact, a significant portion of Earth's surface is on fire. Flames rage on multiple continents at once. The smoke from these countless fires combines with the dust thrown up by the impact itself, forming a choking blanket in the atmosphere. Daylight turns into an uncanny dusk beneath a veil of black smoke. The sun, struggling to penetrate the thick haze, appears as a feeble reddish orb in a darkened sky. As the first night after the impact falls, that darkness deepens further. In many regions, it becomes nearly absolute. No moon or stars are visible through the ash-laden clouds, and the only illumination comes from the dull, hellish glow of distant fires on the horizon. The world has been set ablaze and plunged into darkness at the same time. And it is not just the fires. The impact's shockwaves continue to reverberate through the Earth itself. Powerful earthquakes ripple across the globe, some triggered directly by the colossal jolt, others as aftershocks and sympathetic failures of stressed faults. Landslides rumble down mountains, hundreds or thousands of miles from the impact. In some regions, dormant volcanoes feel the disturbance. A few might sputter to life, awakened by the passing seismic waves. The entire planet rings like a bell that has been struck by a giant hammer. For hours after the impact, and in some places even days, the ground keeps trembling intermittently. These aftershocks are a continuous reminder that the Earth is still trying to settle from the colossal blow it absorbed. In the oceans, the colossal tsunamis generated by the impact race outward, wreaking havoc across the seas. One by one, far-flung coastlines experience the onslaught of towering waves. Hours after the collision, a wall of water reaches shores on the opposite side of the ocean from the impact. Low-lying islands are swamped as the sea rises violently to swallow them. Coastal cities, unaware of the distant cause, suddenly find the ocean surging into their streets as multiple waves crash ashore. Ships in ports are lifted and hurled inland, tossed about like toys in a bathtub. Even continents separated from the impact by thousands of miles experience strange tides. The sea first withdrawing, then rushing forward in a devastating flood that obliterates harbours and seaside communities. The echo of the impact's fury carries to every ocean basin, the crashing of distant waves, a final testament to the asteroid's global reach. In the midst of all these immediate catastrophes, an even more pervasive threat is taking shape high in the atmosphere. The fine dust and aerosols injected by the blast, along with the soot from all the burning forests and cities, are spreading around the globe. As the initial glow of re-entering debris subsides, it leaves behind a sky filled with particles. Within days, a murky shroud of ash encircles the entire planet. Sunlight is severely dimmed. What should be bright noon becomes a twilight gloom. Across the world, days take on an eerie half-light, and nights are pitch black under this blanket of debris. The atmosphere has been poisoned by dust and smoke. When clouds form, they carry this poison. Soon the rains that fall are dark and acidic, laden with sulfur and nitric acid from the vaporized minerals and burning air. These caustic rains scorch leaves, turn lakes and rivers acidic, and leach nutrients from the soil, compounding the environmental disaster unfolding below. Temperatures around the world begin to plummet. With the sunlight struggling to break through the thick pall of ash and smoke, the surface of the Earth cools rapidly. In the weeks following the impact, a chill descends even over regions that are usually warm. Days that once baked under a tropical sun now feel like dim, cold winter afternoons. Crops that somehow survived the fires are stunted by the lack of light and warmth, and soon they wither in the strange cold. The planet has entered an impact winter, a long, frigid night imposed on Earth by the debris lingering overhead. This unnatural winter could last for months, even years, until the skies finally clear. For now, every passing day grows colder and darker than the last. Beneath the thick, dark skies, life faces an extreme struggle. Many animals and plants that survived the initial blast and the fires now find their world utterly transformed. The air is dusty and hard to breathe, irritating lungs and reducing visibility to a dull haze. The ground is blanketed by ash, and the once green landscapes are grey and silent. Sunlight, the fundamental energy source for ecosystems, is nearly absent. Days pass in a murky twilight, barely distinguishable from night. For the survivors, it is as if the sun has abandoned them. The psychological weight of ceaseless gloom is as heavy as the physical hardships. A drizzling rain of ash occasionally falls from the darkened heavens, coating the world in a fine grey powder. Even in far northern and southern regions, the snow and ice are darkened by soot. No corner of the globe is completely untouched by the fallout. Across the globe, ecosystems begin to collapse. Plants cannot photosynthesize in perpetual dusk. Many die within weeks, their reserves exhausted, and no sunlight to sustain them. Forests that endured the fires now slowly die standing, leaves turning brown and falling in the cold gloom. Without plants, the herbivorous animals have no food. They starve or weaken, their populations dwindling. And without herbivores, the carnivores likewise face famine. In the oceans, the same chain reaction unfolds. Microscopic plankton, starved of sunlight, collapse in number. The fish and larger sea creatures that depend on those plankton either migrate in desperation or perish as their food source disappears. From the tallest tree in the rainforest to the smallest algae in the sea, the base of the food web is failing everywhere. The great machinery of the biosphere is grinding to a halt. The darkness brings not just hunger, but bitter cold as well. Deprived of the sun's warmth, the Earth's surface cools day after day. A damp, pervasive chill settles over the planet. Regions that once knew only warmth feel the sting of frost. In tropical areas, thin layers of ice glaze ponds and rivers on what should be hot summer mornings. Snow falls in places that have never seen it before. Faint flurries dusting the rainforests and a white coating on deserts at night. It is as if the world has been thrust into the heart of winter overnight, regardless of what the season was before. As this impact winter deepens, any life that somehow survived fire, flood, and quake must now endure freezing temperatures and perpetual night. Only the hardiest or luckiest organisms have a chance, and that chance dwindles with each sunless, frigid day. Week by week, the new world remains locked in this dark freeze. The great fires that raged across continents gradually die down, having consumed everything they could burn. They leave behind vast stretches of charred and smouldering land. Where forests once swayed and cities once stood, there are now only blackened stumps and ruins, blanketed by ash and dust. High above, the haze of particles still cloaks the sky. Even when flames no longer light the horizon, the days remain dim. Occasionally the sun shows through as a weak, rust-coloured disk, offering little warmth. Most of the time, it is obscured entirely. The moon and stars, too, are hidden on nearly every night, leaving the nights doubly long and oppressively dark. In this sun-starved world, a profound silence often reigns, a silence born of the absence of life and activity that once filled these landscapes. As months go by in this state of twilight and winter, the toll on life becomes ever more stark. Scientists in the far future would recognize this time as a mass extinction in progress. The great and the small alike succumb. The mighty creatures of our modern world, the largest mammals, the apex predators, the abundant birds and fish, are now dying in droves. They face the same fate that the dinosaurs did 66 million years ago, when a similar impact shrouded the Earth. In once lush forests, there is an eerie silence. No bird calls, no insect buzz, only the creaking of dead trees in the cold wind. The ground is littered with the carcasses of animals, large and small, that could not find sustenance. In the oceans, corpses of fish and marine mammals wash up on barren shores. Even the great whales and dolphins have fallen silent in the empty seas, unable to find sustenance. The diversity of life is shrinking rapidly. An extinction event is unfolding before the planet's eyes. Humanity, despite all its technology and foresight, finds itself struggling to survive this apocalypse. In the first hours and days, hundreds of millions may have perished from the direct effects: the blast, the raging fires, the tsunamis. Now, in the following weeks and months, many more succumb to the secondary effects. Crops fail under the ashen skies. Famine looms. Clean water grows scarce as ash contaminates rivers and reservoirs. Disease begins to spread in the weakened, displaced populations. The fabric of human civilization, already torn by the immediate catastrophe, continues to unravel in the darkness. Communications falter and then cease. Power grids have collapsed, and governments struggle to function from deep shelters or not at all. Cities that once blazed with light every night are now dark and silent. The great cities of the world, once bright and bustling, are now ruins draped in ash, their landmarks and towers blackened or collapsed, their streets empty and quiet. In many places, communities are cut off and left to fend for themselves in a hostile, transformed world. The achievements of centuries, electricity, commerce, agriculture, have been set back into a primitive fight for basic survival. Humanity hangs on by mere threads in a sunless world, awaiting a dawn that is slow to return. Yet, in spite of this grim tableau, not all hope is lost. Even as the global catastrophe reaches its darkest moments, small pockets of life endure. Not everything was destroyed in the initial inferno. Some seeds lie dormant in the soil, insulated from the searing heat, waiting for their chance to sprout. Some animals found refuge in deep burrows or caves underground, shielded from fire and blast. In the depths of the ocean, far below the turbulent surface, marine life clustered around hydrothermal vents continues its quiet existence, oblivious to the chaos above. Life hangs on in these cracks and crevices, in deep pools and hidden corners of the world, biding its time until conditions improve. Among humans, too, there are survivors. A fortunate and prepared few managed to take shelter in bunkers, mines, or sturdy underground facilities as the impact drew near. They stockpiled food, water, and oxygen, and now they cling to life beneath the ruined surface. In remote areas far from the impact, some communities weathered the initial blasts and have banded together to survive the dark winter as best they can. They ration their supplies and share warmth around makeshift fires, determined to outlast the long night that has fallen over the earth. In those flickering shelters, people comfort one another with stories of the old days and promises that the sun will rise again. Through fear and hardship, they keep hope alive, waiting for the eventual dawn. Time marches on, and gradually, the immediate horrors begin to relent. After several months, the thick dust and soot in the upper atmosphere start to settle out. Gravity pulls the heavier particles back down, and rain, even if acidic, washes some of the ash from the sky. Bit by bit, the blanket of darkness thins. Perhaps half a year or more after the impact, the first true hints of sunlight break through in parts of the world. Pale rays of sun beam down through ragged gaps in the cloud layer, feeble but real. Those who survive emerge from their shelters and blink at the brightness, some raising their hands in astonishment, some weeping with joy to feel the sun's warmth on their faces for the first time since the catastrophe. For a moment, it is like a dawn of a new world. With the return of even a modest daylight, the frozen world stirs. Temperatures climb slightly now that sunlight filters in again. In places where the soil still holds seeds and roots, the miracle of life quietly resumes. Tiny green shoots push up through ashen ground, frail at first, but persistent. Hardy grasses and small weeds, the pioneers of devastated land, begin to carpet patches of the wasteland with a faint flush of green. In burned forests, new saplings germinate among charred stumps. Ferns, nature's vanguard in ruined landscapes, unfurl little fronds wherever they can find moisture and a hint of light. Here and there, a dusty grey expanse is punctuated by the soft green of new growth, a delicate promise that the land can heal. As plant life returns, however slowly, it brings a ripple of recovery through the battered ecosystems. Insects reappear, some from eggs or cocoons that survived buried in the soil. They find the budding plants and begin to pollinate and nibble, starting their lives anew. Birds, those that survived by flying long distances to escape the worst, or by sheltering in protected niches, begin to venture back, drawn by the emerging greenery and the insects they feed on. Small mammals, the ones that hid deep in burrows or survived on stored food, creep out of their holes and cautiously nibble on the fresh shoots. Each tiny resurgence, a bee buzzing around a new blossom, a bird's chirp echoing in the quiet, a rabbit's tentative hop across scorched ground, is a step in the healing of the world. They are affirmations that life, though beaten down, is not broken. On the human front, the survivors also take heart in the returning light and warmth. Communities that persevered through the endless night now cautiously emerge into the changed landscape. The cities they once inhabited lie in ruins, blanketed by ash and eerily empty. But within those ruins, they search for anything that might help them start again. Canned food, medicine, simple tools, all are treasures in the quest to rebuild even the simplest comforts of life. Under a dim but growing sun, people begin to clear debris. They light small fires, not just for warmth and cooking, but as beacons of normalcy returning. Slowly, carefully, survivors reach out to one another across the silent distances. Using hand-crank radios or scavenged generators, they send signals into the quiet air and listen for replies. And when, in that vast silence, a crackling voice is finally heard from another settlement or a distant hill, tears of relief and joy flow. Humanity realizes it is not alone. Across ghostly plains of ash, the spark of civilization endures in these tenuous new connections. Earth's climate, though deeply disrupted, starts to slowly stabilize as more of the skies clear. After a year or more, the sun shines on most days, at least weekly. Rain and wind gradually cleanse the atmosphere and the land, washing much of the remaining soot into rivers and oceans. Bluish patches return to the sky, where thick clouds of debris dissipate. And with them comes the remembered warmth of day. Seasons begin to regain some of their former rhythm. The world's weather is not exactly as it was. Colder years will linger, and odd, unseasonable storms will still sweep the globe. But the worst of the impact, winter, slowly lifts. With each month of clearer skies, the biosphere inches further toward recovery, as sunlight and rain nourish the revival. Forests that were burnt begin to sprout anew. In some places, only skeletal black trunks remain from the old growth, but around them, life is returning. Grasses and shrubs spread first, covering the ground in green. Then come fast-growing pioneer trees. In a few years, young groves tremble in the breeze, where silence and ash once reigned. As time goes on, these saplings will thicken into woods, and eventually, forests will cloak the land again, different than before, but full of life. Rivers that ran dark with ash begin to run clear. Little by little, aquatic life creeps back. Hardy fish from less affected streams swim upstream. Frogs and salamanders reappear in the shallows, and insects skim the water's recovering surface. The oceans, too, show a pulse of renewal. Sunlight penetrates the surface waters again, allowing tiny plankton blooms to cautiously resume. In turn, small fish gather to feed on them, and larger creatures follow. The great marine food web climbs slowly back from the brink, step by step, as survivors colonize the empty niches of the sea. Throughout the planet, evolution and adaptation carry on in the wake of the cataclysm. Many species are gone forever, victims of the asteroid's wrath, but those that remain begin to fill the empty niches left behind. In the absence of former competitors or predators, surviving creatures expand their ranges and diversify into new forms. Over many generations, life adjusts to the altered world. The planet, though scarred, starts to teem with life once more, a mosaic of hardy remnants of the past and new species emerging to shape a novel ecosystem. The grand tree of life, though pruned severely by the disaster, begins to branch out again, green and alive. Human survivors face immense challenges, but they too show resilience and ingenuity. After the initial year or two of pure subsistence and survival, people slowly shift focus towards rebuilding what was lost. With much of modern infrastructure gone, they find themselves relearning fundamental skills. How to grow crops in soil that is thin and ashy, how to purify water that is tainted, how to construct shelters using salvaged materials and what nature provides. Communities migrate or consolidate around places that offer fresh water, arable land, or shelter from the still harsh elements. Perhaps a valley that escaped the worst ashfall, or a lakeside where fish have returned. In those havens, the remnants of humanity set down the seeds of society once more. In time, small settlements take shape, humble but hopeful. Tents and makeshift huts gradually give way to sturdier cabins as survivors make bricks from clay or cut lumber from the young forests. These settlements become beacons of human persistence in the empty expanse. Families grow again. Children are born who never saw the world before the impact. They grow up under skies clearing of ash, hearing only stories from their elders about the time when a star fell from the sky and turned the world upside down. At night, under the gradually brightening stars, those who remember gather the young around campfires and speak in hushed voices of the bright day that suddenly turned deadly, of the long night that followed, and of the blessed mornings when sunlight finally returned. As the environment heals, so too does the spirit of those who survived. What once seemed like an endless nightmare has slowly given way to routines of living once again in this changed world. There is deep grief for all that was lost, loved ones, homes, entire species, but also gratitude for the second chance that remains. People take solace in the small blessings around them, the sound of a bird singing in a newly green tree, the feel of real sunlight on their skin, the taste of the first fresh berries, or loaves of bread baked from grain harvested after the famine. Communities come together to celebrate these humble harvests. A simple meal shared becomes a profound thanksgiving for survival. Over the years, the Earth's physical scars begin to soften under new growth. The gigantic crater left by the impact still gapes, a stony reminder of the cataclysm, but even it begins to transform. Rains fill it with water, turning it into a lake. Vegetation creeps around its edges, hardy shrubs and vines stabilizing the raw soil. In a few centuries, that crater might host an oasis of life all its own, a tranquil lake ringed by forests, a strange new sanctuary born directly from destruction. Life's resilience reveals itself not only in the broad strokes of forests regrowing and seas replenished, but in countless small, poignant moments. A single green shoot pushing through a crack in blackened earth, the first call of a cricket or frog returning to a once silent night, the laughter of children playing among ruins now softened by weeds and wildflowers. Each of these is a sign that, despite the worst imaginable upheaval, the thread of life was never truly broken. Against all odds, it continues to weave a future. Civilization, too, begins to stitch itself back together, slowly but surely. The survivors carry precious knowledge of technology, of science, of history, and piece by piece, they apply it to their new reality. Old books and digital files, salvaged from the ruins, become treasured guides on how to till the soil, how to generate electricity on a small scale, how to treat illness and injury. Over generations, humans painstakingly relearn and reinvent what was lost. Though the journey is arduous, bit by bit, they reclaim some of the advances and comforts of the past. Villages and towns form networks with each other, trading goods, sharing knowledge, and ensuring that the memory of the old world's lessons are passed on to future generations, guiding the new society taking shape. Throughout this long rebuilding, humanity, and all life on Earth, lives under the shadow of what happened. The memory of the great impact becomes a caution whispered across campfires and eventually written in new history books. The night sky is once again brilliant with stars and seemingly peaceful, yet it is the same sky that delivered the terrible visitor. People look up at those stars with a mix of renewed wonder and deep wariness. They remember that from the tranquil heavens, a mortal threat once arrived without warning. They know it could happen again, someday in the distant future. And so they resolve to be vigilant, to watch the skies as well as cherish the earth, determined that their descendants will not be caught unprepared if the cosmos ever tests them again. Yet along with that caution comes a profound appreciation. The cosmos, for all its dangers, still holds immense beauty and mystery that humankind has always sought. Under the glittering band of the Milky Way on clear nights, perhaps around a small fire, survivors and their descendants reflect on the events that nearly ended their world. They take comfort and meaning from the fact that, against overwhelming odds, life endured. They pledge to cherish their fragile world anew and to protect it and each other with a fierceness born from knowing how precious and tenuous life can be. From the ashes of annihilation, the story of Earth continues. In time, much that was lost is regenerated or reinvented. Forests once again blanket the land, rich with the descendants of those plants and animals that survived. Creatures great and small roam among the trees and plains, some reminiscent of the past, others entirely new, the products of evolution's unpredictable creativity. Human societies rebuild homes and cultures. They may be simpler at first, but perhaps they grow wiser and more unified, bonded by the shared legacy of the catastrophe they overcame. The world that emerges is forever changed and carries the scars of what happened, but it is also a world given another chance to thrive. The tale of the asteroid impact becomes a sober testament to nature's destructive power and to life's incredible tenacity. It reminds all who hear it that every living thing exists by geological consent, subject to change without notice. And yet, even when the worst imaginable event occurs, even when nearly all light is extinguished, life finds a way to rekindle. The Earth has experienced unfathomable devastation, but it has also seen renewal. This cycle of destruction and rebirth, etched into the planet's history, has now been witnessed firsthand in our time. In the end, what remains is a world humbled but healing, scarred but very much alive. The asteroid arrived as an unthinkable catastrophe. For a while, it truly seemed like the apocalypse had come. But after the profound darkness, light returned. After widespread death, life began again. In this fragile rebirth lies a promise. As long as even a few living things persist, the story is not over. The chapter of this great impact draws to a close, and a new chapter of recovery and growth begins, carrying forward the legacy of the survivors and the memory of those lost. Above, the sky once more shines blue by day and reveals an eternity of stars by night, a gentle reminder that even after immense tragedy, the world can find its balance again, and the saga of life will continue